All right. Uh, Good morning, everyone. Good afternoon, whatever time zone you're in. Good evening. Welcome to the what we hope is the first of many ODSA workshops and accelerators. And we the first thing I want to tell you is that our group, everything you see here today, is a result of active and significant community collaboration, as is the entire OCP. So this is a workshop organized by the ODSA, the Open Domain Specific Architecture Subgroup, which sits at the intersection of chiplets and accelerators. Most of our prior workshops are concentrated on chiplets, and we hope to do a sequence focusing on accelerators. And this one is focused on storage acceleration in particular. I want to thank JP. I want to thank JP and Quinn and Ravi and Young for this huge efforts in getting this workshop organized, and the OCP as well, for all the excellent support from Michael and Kaylee and everyone else. One important thing, Quinn will be running a survey in the last session, so please, we would really value your participation in that survey. So what I'd like to do is spend a couple of minutes on what the ODSA is about. So the group itself, sits at the intersection of two interesting trends in compute. The idea that you need domain-specific architectures to accelerate compute-intensive workloads. So the general sense that what you need is beyond the general-purpose CPU sitting in data centers, that you need video accelerators, machine learning, the inferencing accelerators, compression engines, whatever else, in order to accelerate performance of specific workloads. And the idea that these accelerators can be economically and rapidly achieved with an approach based on designing products using chiplets. So the idea that basically rather than designing these accelerators as monolithic devices, you can actually design them as a collection of die in a package. Now, what makes the ODSA different is that today there's a whole bunch of chiplet-based products in high volume production today. But most chiplet-based products in the marketplace actually integrate chips die from one vendor. What we'd like to do is enable the creation of open interfaces for chiplets so that you can assemble DSAs with best-in-class chiplets from multiple vendors. Roughly, our charter, we have three broad categories of work. The first is the definition of an open die-to-die interface. So if the idea being that if chiplets that support this open die-to-die interface can more easily interoperate. We have several publications on this, and I won't spend any cycles on this interface in this workshop. And the second bucket is reference designs. The idea that, if we glue together, and that's what this workshop is building off, we have a fantastic POC, hardware POC that you'll learn more about that integrates products from multiple companies. And the idea is that these reference designs, and we also have a test chip in flight for one of the interfaces we're defining. So we have a bunch of activities designed to get the community off to a start in using chiplet-based designs. And finally, the third leg of our activity is reference workflows. The idea that chiplet-based design is different from standard monolithic design, and that you need reference workflows for companies to do business and for production workflows. The end result of all this should be a chiplet marketplace where product designers can integrate best-in-class chiplets from multiple vendors through these open interfaces, starting with these reference designs and using these reference workflows to actually produce their product. And what we want is for all of these to land in the various OCP form factors. So there's a bunch of information about all this in our wiki. So I can't stress enough, please go to the wiki, and whatever you need, we have it at the wiki. Our activity, we have about 8 work streams, which I haven't listed here in the interest of time, but we have work streams for each of these categories. So we have about 3 work streams, 2 dealing with die-to-die interfaces, 1 dealing with a link layer in the idea of an open die-to-die interface. We have a POC work stream, we have a business work stream, and a CDS work stream that deals with reference workflows. So all of these work streams meet weekly. We also have a weekly meeting on Fridays at 8 a.m. This workshop is taking the place of our weekly Friday meeting. So if you'd like to find out more, please join us at these Friday meetings that are open to all. Help us with anything in particular. In this workshop, we'd really like more of your help in the POC and developing software for the POC. And ultimately, our goal is to translate the POC into a chiplet-based design. We have at the upcoming OCP Fall Summit, we have first off, the OCP has a summit coming up in the fall, which is the first in-person summit again, so everybody's kind of excited. And in that summit, we have a 4-hour engineering workshop devoted to the ODSA. So please join us at that, both for the Fall Summit and the ODSA engineering workshop. We have a rather tight agenda today. Actually, a really busy, really good agenda. Beyond that, immediately after me, we'll have Zhang from Samsung talk about how we see ODSA accelerators reducing TCO. Then we will jump right into introducing you to the POC. And we have a really experienced group of speakers from different facets of industry in storage, all talking about different aspects of storage accelerators. Ideally, what we'd really like is for some of you to be able to please join us in this collaborative effort and help us in building a POC and demonstrating it at the Fall Summit. So we have the hardware. We'd love to be able to sort of take this hardware and show something at the Fall Summit with the hardware we do have. We're kind of tight for time. We have an extraordinarily crowded agenda for a 4-hour workshop. So to keep things moving, if you have any questions, we'd like questions. What we've done in previous workshops is have an entire follow-on session at our weekly meeting where we address the questions and the speakers come back. But if you can, please enter your questions in the chat window in the GoToMeeting, and we'll get to some of them. Those that we don't get to, we will eventually address for sure. I promise you that. With that, I don't want to stand in your way. If you have any top-level questions, please feel free to reach me through the OCP. Or type them in the chat window and I'll get back to you. And that's about it. Zhang, I think it's all yours.
Okay, can you hear me?
Yep, let me stop sharing my screen for a second.
Sure.
Wait, stop sharing. Michael, I think you'll have to disable my screen sharing because I no longer see the option.
That's okay, Zhang's already set up.
All right, thanks.
Okay, can you guys see my slide deck?
We do, yes.
Okay, just want to make sure we're on the same page. Hope everyone's doing well in these troubled times. My name is Zhang Paik. I'm a senior director in product planning here at Samsung Semiconductor, based in San Jose. And today, what I wanted to kind of give people an idea of is how we should be taking a look at the value of an ODSA device. So it's one thing to say that I can reduce costs, but let's take a look at the overall picture, because I think that sets the good stage for some of the other sessions that we have today. So to start with, there's the standard legal disclaimers. I won't be talking about anything that's really Samsung specific right now. I just want to get some high-level ideas across, so no real worries here. And the first thing I wanted to start with is that we do have experience in terms of trying to move compute outside of the CPU. And one of the concepts that Samsung took a look at quite a while ago was something called the KV-SSD. A big problem that exists today in computing is that all of the work is being pushed into the CPU. And there has been work to try to move it out. And one of the things that we wanted to test and see was if we got rid of the block operations and moved those into the SSD, into a KV-SSD, what would happen? A well-known phenomenon amongst a lot of our customers is that a CPU will saturate at around 4 to 6 SSDs. SSDs are just increasing in performance very, very quickly. And as a result, as you begin to add drives, you hit saturation fairly early on. And although a server can handle up to 24 fairly easily nowadays, the CPU can't handle all that traffic. So we reach a point of saturation fairly low on. And in our early experiments, we were able to find that the KV-SSD does help. Now, this is far from the end of it all, right? It does depend a lot on the use case, but take this as just kind of a lab experiment to see, does this actually help? And we did find some very interesting cases for this. So one of the things that we should take a very close look at is the state of accelerators today, right? There are a lot of them in use. We have different kinds like SmartNICs have been used for quite a while now to offload network functions, handle encryption, and all of those functions are generally moved from the CPU into the NIC, and the CPU is now free to do much more interesting workloads. GPUs, which for a long time have been great in gaming and for making images and videos and things like that, and nowadays are being used for AI and ML. Those are great, but they're incredibly parallel, and unless your workload is very, very parallel as well, you won't make very efficient use of the GPU. FPGAs have been very flexible, but they're limited in clock speed. You can't go very fast on them. And the last is the ASIC, which are great in terms of being able to have a very specific task and get great performance out of them. So they're faster than FPGAs in general. The problem has been that they're very expensive to design and manufacture. So this is where the chiplet technology that ODSA is working on kind of comes into play. We really want to take a look at how do you reduce the price of manufacturing an ASIC and making it also easy to develop software on top of. So these are some of the different goals that we have in this project. So some of the questions that I've actually been posing are, well, what is the real value in this? So let's take a look at a couple of different ways that you can make use of an accelerator. And there are two basic forms of doing this. One is that you expect the accelerator to give you better performance. And that's kind of to be expected, right? A GPU will definitely handle GPU type workloads much better than a CPU and et cetera. So some of the examples that we can think about on this is if you can put an accelerator into your server and get 3 times the performance, clearly that's kind of a better solution. Whether or not it's cost effective is a different matter. In practice, what I have found in talking to many people over many years is that better performance is definitely better, but in terms of making it cost effective, the performance benefit is not always clear to people. So if you do have an accelerator that will boost database performance, maybe triple the database performance, but they tell you that the performance was actually fine before, you're just asking them to spend more money. And that definition of better performance and the value of the better performance varies greatly from customer to customer. So it's very hard to assign a value to better performance. Another angle to take a look at this is better TCO. If you're able to make better use of your servers and of your data center space, and you can actually quantifiably say, well, you know what, I can reduce my costs by 10 or 20%, that's a much easier argument to make with a CFO, right? So these are the two different ones. These are not mutually exclusive. So please understand, I'm not saying that you have to choose one or the other. It's just that the better TCO is an easier one to make. And if you find that the TCO is an easier one to make and you can get better performance, so much the better. And so there are a lot of aspects to this that you really have to take a very close look at. You really need to dig under the covers and understand what is the value, what are the cost structures look like, and these are some of the things that I've been taking a look at for the past few years. So here's an example of a TCO use case, and we do have to make some assumptions here. So let's say that we have an ODSA accelerator and we want to process 1 petabyte of data, okay? So we've got an accelerator that sits in front of an SSD in some way, and we're going to process 1 petabyte of total storage. If we assume that the ODSA accelerator will add about 25% to the cost of the SSD, obviously the storage component will be more expensive. There's no getting around that. But there are other ways of saving money, and that's kind of why I'm showing you this spreadsheet here. The other assumption that I want to make, and this is not necessarily a great one, is that the performance of a single ODSA server is the same as 4 standard servers. And what I mean by that is a single ODSA server with 24 SSDs has the same performance as 4 standard servers with 6 SSDs each, right? So the capacity of those two would be the same in terms of terabytes of storage, but the performance is going to be at least comparable. So I'm not looking for any real acceleration of the data here. So as we step through the spreadsheet, we can see that the base server cost without the SSDs, let's say that they're the same. The capacity per server is going to be much greater for the ODSA server because we can put 4 times the capacity of the SSDs, right? We can put 24 of them on instead of 6. And what that means is for that 1 petabyte of data, I need far fewer servers. In this case, I can make this roughly a 4-to-1 ratio. Now, the total cost of these SSDs, as I said, it's going to be 25% more expensive. So rather than 200K, it's going to be roughly 250K. I'm making some ballpark estimates in terms of the cost of the storage. And so the base server costs are much higher on the left-hand side, on the traditional system. And that's something that is a big deal, right? So the storage itself is going to be more expensive, but the cost of the servers are actually higher on the left-hand side. In the end, we'll actually save some money just in that. However, and this is a very important thing to understand, there are additional costs, and one of them are the host maintenance costs. So here I'm assuming roughly $4,000 a year per host to maintain, and we're talking about hiring an admin, a person to manage these servers. And $4,000 a year per server is not, it's unfortunately not a great estimate because it can be more or less depending on your use case. I've seen numbers much smaller than that. I've seen numbers much larger than that. Again, it does depend, but that's kind of why you create these spreadsheets. And those costs are dramatically reduced because of the far fewer number of servers here. And in the end, what you will find is that the TCO will be greatly reduced. So in this case, I'm seeing a 60% TCO reduction. Now, a couple of additional notes here that I didn't take into account. One of them being that another aspect of saving money is that when you have fewer servers, you need fewer network ports, and that simplifies your networking. You can also put more capacity into a single rack, and that also can reduce your overall cost. And I haven't taken power into account either. And again, you have to go through the calculations to see which of these might take more or less power. In general, we found that when you add an accelerator and have this sort of an architecture, you do use a little bit less power. So these are all great benefits. And in the end, the other thing to understand is that even if you get slower performance, right? So you may not get the same performance here on the ODSA server as 4 servers, but you might actually find that it's still a better solution. And again, you won't understand that until you go through the full set of calculations. So all I'm suggesting here is that there's been a lot of work going on to minimize the cost of creating a chip, an ODSA type chip using chiplet technology. We recently got a talk at the ODSA meetings from Google where they talked about the cost difference comparisons between creating a chip using a monolithic die versus chiplets. And they're not saying one or the other in terms of which is actually cheaper necessarily, but they have gone through the pain to understand what the cost differences are in making the chip. And what I'm going through is what the TCO is in terms of using the chip. So they're slightly different use cases, but you need to go through everything to understand what the real benefits are. And finally, what I kind of wanted to wrap up with is, what will the future bring? And chiplet technologies, the main goal here is to make it a lot faster to create these accelerators and much cheaper. And in addition, we're going to need an ecosystem of partners in all of this. We already in the ODSA group have a number of different companies who are willing to contribute IP, basically their own chiplets, and we're going to need more of those. And maybe even more importantly, it's going to be to make the corresponding software. So when you put these chiplets together, you already have some base foundational software that you can base your new solutions on. And so we're going to need partners that are able to create, CPUs, GPUs, maybe some sort of a neural processor, NPU, networking, FPGA. There may be other ones out there that I've never even heard of that you can put into an ODSA device, create those chiplets, and hopefully we'll be able to have a software infrastructure that will really allow this to explode. So with that, I think I just wanted to go through this very quickly. My name again is Young Paik. Please let me know if you have any questions.
So I'm Quinn Jacobson. I'm the moderator for this morning. If you have questions, please just type them in the chat window and we'll address them.
No.
No questions. Okay. Well, thank you very much, Young. Let's maybe go ahead and we'll have time at the end of the conference for a broader discussion, also have follow-up questions to any of this. So if there are questions that you realize later on, please either throw them in the chat or just remember them, because we do have a session at the end, basically just reserved time to have a conversation. One quick question, Young. We're looking at storage. Do you think that is potentially one of the best TCO use cases for accelerators?
I would say that storage definitely is. There is already a lot of work being done in computational storage. In fact, I think we invited the SNIA computational storage session or people in that into this meeting today. Computational storage is very, very challenging. And one of the aspects to this, again, if you take a look at a server that can do 24 SSDs, and you think about the bandwidth that is theoretically possible, right, with PCIe Gen 4, you can get upwards of 7 gigabytes a second per SSD. That's 168 gigabytes a second into a CPU or a pair of CPUs. And that's clearly far more than CPUs can handle today. So by moving some of the work from the CPU and into the SSD, in theory, you might be able to make much better use of that processing. The one thing I caution people on is you can't move everything, right? You can't turn the SSD into a little server, at least not easily, and expect the same kind of performance you would from a Xeon processor. So this is where we have to be a little bit cautious and make sure we know where to place what kind of computational work. That will probably depend on the use case. So in some cases, people will want a lot more power in the use of the SSDs. They're going to need kind of a bigger chiplet, if you will, something with more computational power, and they'll design the server that way. Other people might want very little amounts of work, just handle the block operations or something like that, and then pass that data into the CPU. That might get you the acceleration you need. I would say that computational storage is definitely one of the more interesting types. We actually could see that with any one of the different kinds of chiplets that we see, the CPU, GPU, and et cetera, for the pre-processing of data before it gets into the CPU.
Yeah, I think it's important to note that you really want to make sure that as you're moving to these more domain-specific areas, that you're accelerating the workload, not just moving it to maybe even slower at doing the same work.
Yeah, well, like I said, it is possible that you can still get benefit, but you don't want the overall workload to get slowed down too much. As long as you do the calculations and you've done the testing, you should find that there will be benefit.
Excellent. Any other questions from chat? I don't see any right now.
Hey, Quinn, we actually do have one other question, just came in.
Okay.
From Vincent Mute. Are there any other good production examples where disaggregation is helpful and the co-design and programming is not too expensive?
Oh, those are two things that are not quite mutually exclusive, but one of the big areas that I see also that is not in computational storage or along those lines is in AI and ML. So today, when you take a look at a lot of the training that goes on, you take a model, probably in a GPU, maybe in a single GPU, and it's kind of a monolithic problem. You have the GPU doing a tremendous amount of work. Especially when it comes to these larger models, it may be advantageous to take advantage of different kinds of computational units, right? So you might have something that's better in a GPU, you might have something else that's better in an FPGA, and it depends again on exactly the kind of models. Some of them require a tremendous number of input parameters, and they can be handled in parallel. Others require very few, but they have a much deeper model. So when you do your evaluation of the models, you can take many different kinds of things into account and do your training or your inference in a server. So by having an ODSA chip that does many of these things together, you could wind up with something that's better than a pure GPU solution or a pure FPGA solution. So I think that's definitely one use case. The challenge there, though, is that the software is still has to be written for those kinds of things. I would say that there's a lot of work being done in that now, so entirely possible that people are already starting to make that a lot easier.
Thank you. So I think we're kind of at time here. We're going to do our best to stay on schedule today. So with that, thank you very much, Zhang. And we will ask, JP and Vijay are up next to discuss the Open Data Accelerator hardware, which is kind of the main event maybe for this workshop. So with that, I'll turn it over to you guys.
Thank you, Gwen. So that was an interesting talk from Zhang on accelerators for TCO reduction. We'll now switch gears and talk about, let me share my, and talk about the accelerator prototyping platform that we have been developing at ODSA. So I'll be joined by Vijay and Shakti from Tamind. First, I'll give you a high-level overview of the platform architecture, what the platform does, and what led to the platform development. And then I'll hand it over to Vijay and Shakti, and they will do a demo of the platform. Yeah. So, so this platform, so we have been developing for quite some time now, and this would not have been possible without the active support and contributions from multiple companies involved, shown here in this slide. So we thank you for all the contributions and collaborations for all the partners involved in this particular project. So first, let me start with high-level trends indicating why we started developing this prototyping platform for accelerators. Right. So as Bapi was mentioning, the Moore's law is slowing down, is aging, and so we need different design paradigms to compensate for the slack in performance caused by the Moore's law slowdown. So there are two important solutions that are being adopted in the industry today for the Moore's law slowdown is domain-specific architectures or domain-specific accelerators. The second one is chiplet-based designs. Right, and that's what these two are the trends actually what constitutes the ODSA, the project of OCP. And so this week has been very busy, like with hot interconnects and hot chips. And if you attended the hot chips conference earlier this week, so one of the things that got featured is actually the Intel Ponte Vecchio chip. So this is a monster GPU. I think it's about 500, 600 watts. And so this is actually a poster child for chiplet-based designs. It has 47 active tiles and has the dies from 5 different process nodes from TSMC as well as the Intel. And these dies are assembled just like how would you assemble a package on a PCB. The same way these are assembled using advanced packaging, 2D and 3D packaging techniques. Right. So this is a kind of what we expect to see in future as well. All right, this is kind of extreme with 47 tiles, really a high performance chip. But what is actually the challenge? The challenge here is actually these chiplet-based designs today are done by companies like Intel, AMD. They are vertically integrated. All the chiplets they have today are actually designed by them, and they are vertically integrated. There are no third-party chiplets, at least to our best knowledge, right? So how to proliferate this adoption of this chiplets, just like how you do PCB design today? That's one of the vision of the ODSA. And the ODSA actually develops open interfaces for chiplet-based designs like die-to-die interface, and then it also we also work on the reference designs. Like the prototyping platform you see today is one of the results of this reference design flows. And also the ODSA is contributing to the chip development flows as well. There's a lot of activity going on. Our eventual vision is to get to a chiplet store. Today, if you go to a OCP website, you have a store or a platform where you can buy and sell servers. The same way in future, we envisage the OCP will also host a chiplet store where you'll be able to design a chip by sourcing the chiplets from the OCP store. Right, so this is what we had the vision, and so back in 2008, way back in 2008, this is the concept we had, early kind of proof of concept. So we wanted to build a chip, a package design with 3 different dies from different companies. Right, one is actually a network accelerator, NFP processor, an FPGA, a generic data path accelerator, and the CPU. Right, so this is a concept we had, but there are 7 challenges implementing this architecture. One is actually this is for an open source effort. This is a big undertaking with so many big components like this, and the that problem can be solved given the right resources. It can be solved, but what we felt is a drawback is actually once we actually commit to a package and we put these dies onto it, the design is kind of frozen and there is no expandability, or we can't, let's say, for instance, if you want to try out a network accelerator processor from another design for another vendor, or FPGA, a different design, or CPU, we want to try something new. This architecture did not allow us. It's kind of one-time frozen. And what we wanted really was an architectural exploration platform, right, where we can try and mix, let's say, go to a chiplet store, you bring in different chiplets, try and match, and you start developing software, explore the architectures. And that was actually lacking in this, our earlier POC concept, a package-based design. Okay. So after a lot of deliberations and discussions with many of the volunteers who participated in the ODSA, we ended up in developing a platform that looked like this. So what you see here is actually what we call the Open Data Accelerator platform, and and this is actually a full height, full length PCI card. It's a very large form factor as defined by SNIA. And you can see here there are 3 slots, what we call as a pitchlet A, pitchlet B, and pitchlet C. The 3 different chips that you saw here, the dies you saw here in the previous slide, go as a module here. So this is like a Lego building block. So you can actually bring designs from multiple vendors or multiple designs, and then you'll be able to mix and match, tailor architecture, and explore different accelerator architectures. So there is a thinking behind, and these connectors, what's used here is really high speed and very flexible platform. And we had encouragement from a lot of people who looked at this. And so we'll look at this more details of this architecture, but what it has. And so there are 3 slots, and then you also see there is actually a cable that is connecting to the host server with the PCIe cable, Gen 4 or Gen 5. And so we'll talk more details of this platform as we go along. So let's go into detail. What is inside the platform? Right now we saw the form factor, what it looks like. And so you saw there are 3 modules, and these modules actually what we call as a pitchlet. The reason it's called pitchlet because Chiplet on the PCB is what we call as a pitchlet. Once you actually take a chiplet and package them and put in a PCB, a module form factor, it becomes a pitchlet. And in this platform, we support 3 pitchlets. And you can see here in this diagram, the pitchlet ABC are actually kind of wired to a rich interconnect fabric. It's a fully connected mesh with the high-speed wiring between them. So this in the high-speed wiring supports up to 112 gigabits. The platform has been optimized for very high-speed data rates, so you'll not have any limitations in what you want to explore, and supports any protocol. Is actually a PCI Express or Ethernet or Gen Z. Any case, it's actually a kind of a bunch of high-speed wires. Right, and also the platform is architected such that any clocking architecture, if it's a common clock or you have a separate clock, all this different clocking mechanisms can also be supported through this high-speed wiring. And we also have a generous GPIO wiring. These are high-speed wiring, except we call GPIO because these are single-ended, and that allows you to try different configurations, like experiment with different protocols, or actually if you want to develop some control signals around that, and this is where it would be helpful. And again, these are the GPIOs are also again high-speed cable, length matched, and would allow you to experiment a lot more. Right. So and the pitchlet A and B are kind of special. They can connect to a network like through QSFP ports, high-speed ports, and I mean, it's not, if you want to experiment with the PCIe, that is also possible. For instance, QSFP is only meant for Ethernet today, but if you want to try PCI Express as well, that will also be possible in this configuration, provided you use the right clocking techniques. And the pitchlet C is where we connect an M.2 module. The 2 M.2 modules is connected to a pitchlet C. And you could connect to an M.2 accelerator, like machine learning accelerator, a video accelerator, or you could connect to an SSD, M.2 SSDs, right? And also the platform has got a rich power supply, so it has supports up to 250 watts, and it's extendable. And also it has rich management capabilities. So it comes like a sort of mini BMC where you can control from the host. It'll be able to remotely control the power status and resets. So Vijay will be doing a demo on this, showing he done with Python CLI, which will showcase that. And the pitchlet A will be connected to host via the cable you saw here by a by16 PCI Express link. So overall, this is the kind of high-level architecture. There are 3 pitchlets, and they have a special purpose like M.2s and QSFPs. Right, so this is actually kind of spec. So most of it is what we talked about. One of the cool things about this is pitchlets is these pitchlets are actually interchangeable. You can actually change one pitchlet to the other. And so if you design for one slot, it can work in the other slot as well. There's a detailed spec available, and if you're interested, please contact us. We'll make the spec available for you if you want to design a pitchlet. And so the platform itself is mechanically rugged. This is one thing initially when we start this project, this is going to be a prototyping platform and needs to be very rugged. Chenyu from Facebook helped with the design. It's got a backing plate, stiffener ring, and it is sitting on a nice plexiglass substrate. And it's very easy to use, mechanically rugged. And if you want to do any characterization like temperature forcing, it's possible. It's because of the ruggedized configuration. And the design itself is thermally robust, and we actually close this design for 50 watts of accelerating power, but it has a headroom up to about 100 watts. You can see the temperature, we have a lot of margin, the temperature specs are met. And this work was actually the thermal design, the fan, everything was done by In-Hung from Facebook. And and if you look at the platform signal integrity, it's actually excellent. I was mentioning about 112 gigabits we support, and so this is the connectors and the material that what we use on the board. Actually, it's what this S parameter result shows. and you can see that it has a good signal integrity and you can carry up to 112 gigabits. And so these are the first set of pitchlets. I was mentioning about the pitchlets. These are the first set of pitchlets that came out of this work. One is a Broadcom NIC, and then there's a Lattice pitchlet, and we have a Lattice FPGA and Broadcom 200 NIC, and then there's an NXP also contributed to this with their multi-core ARM CPU. So this is actually the picture of the overall platform. Vijay will go in more details of this platform in his demo. And this is the concept of the storage accelerator implementation. So what you have is it's actually a Lego building block. We took this Broadcom NIC pitchlet and then married with this NXP pitchlet, and along with the Lattice security and management FPGA, and wired them all together. And so along with the PCIe links, and this will form the storage accelerator implementation. And similarly, you can conceive the other architectures. If you want to work on machine learning or other accelerators, you could actually compose with this building block, right? So we also plan to make this setup available for remote development for a 2-node x86 server, along with this the Mara baseboard the setup. And with that, and it forms a 2-node cluster with the high-speed Ethernet links. And with that, you'll be able to access this platform remotely. And if you're interested in development, please feel free to contact us. So next part is actually demo. I'll invite Vijay and Shakti for this demo. Vijay.
Thank you, JP. Good morning, everyone. Hope you're all doing well and keeping safe. I'm Vijay, and I have Shakti with me. We are part of Tamind. We, along with JP and team, have designed and developed the Mara solution for OCP ODSA. We wanted to do a live demo, but it kind of, due to time constraints, in the interest of time, we have pre-recorded a demo for the solution. JP, could you please play the demo? Thank you.
The Mara solution consists of a host machine. We have used AMD Ryzen CPU with 32 GB of RAM and has a X16 Gen 4 PCI Express slot. The baseboard has an edge finger with which it can be connected directly, but due to the size and workability issues, we have connected the edge finger of Mara via an 18-inch 3M PCI Express cable, and due to the length, we have added an Astrolabs retimer to maintain the Gen 4 connectivity. The Mara baseboard has 3 slots for pitchlets A, B, and C. It is powered by a 12-volt power supply. The other voltages that are required are inbuilt. It hosts a 4-port QSFP connector, which is connected to slot A and B. We also have a 2 M.2 slots, which are connected to slot C. It is right now populated with 2 1 terabit Samsung SSDs. The Mara baseboard is supported by an aluminum blaze plate and an acrylic platform for stability, to which the cooling fans and the fan controller are mounted. 3 slots have 2 Molex connectors each, and the signaling is routed in such a way that the pitchlets can be inserted in any slots depending upon the functionality required. On slot A, we have the interposer card, which we have developed to interface between the Mara baseboard and a standard NIC 3.0 card. We have used Broadcom NIC 3.0 card in our solution, which you can see inserted on slot A. On slot B and C, we have the NXP LX2 pitchlet with 16-core ARM processor, 8 GB RAM with customized Ubuntu Linux running. All pitchlets are supported by a stiffener ring. Depending upon the pitchlet bring-up stage, we have JTAG connectivity to all the 3 slots. And if we have the pitchlet at OS level functionality, then through a USB serial converter, CP2108, we have access to the pitchlets consoles. We have developed a Python CLI to remotely control and manage the Mara baseboard features like checking the system status, performing resets, etc. With this, we can conclude the platform overview. Now we are going to see the functional demo of the Mara platform. I'm going to SSH into the host machine using terminal program on my Mac. If you have Windows, you can use programs like Putty. Once you are in, you can verify the presence of the Broadcom card by using LSPCI. ifconfig shows the IP address of the Broadcom interface. The host will act as a router for the two NXP chiplets on the Mara baseboard. If the NXP boards are up and running, you can SSH into the platform, or you can log in using Minicom to the console port. Once you are in, LSPCI will show only the Broadcom interface on slot B. On slot C, you will find the Broadcom and Samsung SSD drives. We can now ping the internet from the NXP. You can also use apt-get install command to install any library you would require for your development. For demonstration purposes, we are going to run some performance test. We are going to run iPerf for network performance, host running as the iPerf server, and the NXP running as client. For testing the solid-state drives performance, we are going to run FIO on NXP. Next, we are going to move to remote management. We have developed a Python CLI for remote management called Mara. You can view the status of the chiplets and the baseboard using the status command. You can also perform a remote reset and other operations listed. This concludes a quick functional demo of the Mara platform.
Actually, I know we kind of ran through really fast, but if anyone would like to have a hands-on experience with the solution, we are planning to host the system for remote access. We are going to put up a sign-up form. We would recommend people to sign up. If you could please sign up, then we'll reach out to you, and then we can actually provide you live support, and you can get into the system and test the system out. And if you wanted to, try something out, you can do it.
Okay, so Jay, should I move to the next slide?
Yes, please.
The Mara solution.
Yeah.
So we are planning to, these are our contributions from Tamind. We are planning to open source the Mara pitchlet and the baseboard design for everyone to use. And we are also going to open source the Mara Python CLI that we have developed. And next one, we are also looking to open source the QSFP assembly tool. Basically, when we were actually trying to assemble the QSFP on the board, we were facing some difficulties. JP, could you move to the next slide? Thank you. So what happened was there was a limitation in the tool that was provided by Molex. When we tried to insert the QSFP, which is a press bit, into the board, we were actually losing the boards, because when you press it, the board was bending and it was causing some problems and the boards were breaking. So we lost close to 2 Mara boards because of that. So then we actually went back to our designs and we actually developed this tool by which then this is actually custom designed for Mara platform, but it can be from the designs, you can actually kind of use it for any platform you develop. So we used this tool. After I started using this tool, we were able to get 100% press fit with the QSFP, and we got 100% success. Maybe the next one.
Yeah.
So you could see the actual assembly tool on the Mara baseboard, and we were able to actually get good yield with it. Actually, we got 100% yield. Thank you, JP.
Okay, thank you, Vijay. That's an interesting work, and especially like the neat little QSFP tool that improved the yield. So in summary, that we have the Open Data Accelerator hardware platform is functional and is proven, and you can access this remote. We encourage you to actually come up with ideas what you can develop on this. And as Bobby was mentioning, we'll be interested in doing some kind of demonstration, the OCP Summit. If you are interested in that, please let us know. And this Mara platform would not have been possible without a great community effort. So it has a robust mechanical, thermal, and signatory designs for a prototyping platform. And we have 3 pitchlets to start with, and we're expecting more pitchlets to come. And if you're interested in designing a pitchlet with your own accelerator, definitely there's something of interest to the OCP and ODSA. Please feel free to reach out to us. And last, importantly, join us to in this effort to advance the data accelerators in the industry. Thank you.
Thank you very much.
Yeah, Quinn, back to you.
Thank you very much. We got a couple questions. I'm going to keep you guys on here for just a minute. I know we're running tight on time, but Michael asked, regarding power delivery to each chiplet, what is your topmost concern or challenge?
So right now that we are feeding 12 volts and 3.3 volts to all the pitchlets. Right, and and you have the point of each individual regulators, like like 1.8 volts or 3. Or lower voltage for each of the components are actually built into the pitchlet itself. So that makes it easier. We can predict what kind of voltages do we need. So we actually kind of fed 12 volts into that, and then the platform itself expect to support that high currents, right? So we also provide a 3.3 volts as well. And one of the challenge was actually closing that 3.3 volts, the current, and that's something we could actually design around that in the Mara platform, because the high currents involved. I think I remember something in the order of about 15-20 ampere range, right? So those issues are resolved, and we have tested the platform with 3 different pitchlets, and it's looking great.
Excellent, thank you. And I think we'll have more questions on these, but let's hold those for the discussion at the end. And I'm going to now hand off to Scott Schweitzer from Achronix on his talk, Data Acceleration Challenges and Opportunities.
Thank you very much. I appreciate it. I'm going to pull back on the stick a little bit and go at a higher level. It's going to be tough to follow JP and Vijay, but we'll do the best I can. I'm going to talk about the challenges and opportunities of accelerators. I'm Scott Schweitzer from Achronix. I've been in the acceleration business for the last 2 decades. Let's go with that. So with that, the first challenge I think we're going to experience is in bandwidth, and we've been seeing this since I joined the SmartNIC accelerator space back in 2005. Basically, the context of this specific slide is going to be SmartNICs, DPUs, and IPUs, and IPUs is Intel's new way of saying DPU. So what we have here on the left is PCI SIG's growth chart for PCI Express from PCIe Gen 1 all the way up to Gen 5. And then underneath that is the Ethernet Alliance's map for Ethernet speeds. And kind of the issue that we've been experiencing with bandwidth on both of these fronts is that Ethernet jumps in aggregates of 10 usually, as you can see from the chart here. There have been some intermediate 4-way interfaces along the way, and actually recently it's 25 and 50 are popped up, as well as 200. But for the most part, it's been jumping in 10s, but it takes a lot longer to move forward. PCI Express obviously doubles every couple of years. So we've had this kind of progression since 2005, when PCI Express Gen 1 and 10 gig both kind of popped onto the scene, and that's actually when I kind of moved into this market space. And everything kind of marched along well from a PCI Express versus Ethernet, alignment. There were every now and then there were a couple of bumps in the road. 40 gig Ethernet came out. It was outpacing things, but it really didn't take up well early on. It was more of a port aggregation switch to switch link than it was necessarily a NIC link up until a few years back. But we're kind of living in the orange space right now, where we've got PCI Express Gen 3x16 and PCI Express Gen 4x16 slots on our servers, giving us between 16 and 32 gigabytes per second unidirectional. And we're matched up for the most part with 100 gig Ethernet on the high-end servers, and that does about 25 gigabytes per second peak across both of those. So orange in the sense that if you're on a Gen 3 slot, you're oversubscribed. If you're on a Gen 4 slot, then you're pretty well balanced. Where it's going to become out of balance over the next year or two is as we start making the jump from 100 to 400, and that silicon is already showing up in the market, or starting to show up in the market. And PCI Express Gen 5, while it's only doubling, Ethernet is going up by a factor of 4, and so as you see, we're kind of outpacing things at that point. So that's going to be a challenge for us. So how do we address that? Right? We obviously throw more computational resource at the problem. These are 3 of the most popular accelerators on the market right now. NVIDIA obviously leads the space in GPUs, and their RTX 3080 is one of a family. It's a foundational member of the family. And as you can see from the stats listed here, the thing has got nearly 10,000. Actually, one version of it has 10,000 CUDA cores, 10 gigabytes or more of GDDR6, and then an extensive internal bus that all that data is humped around on. On the DPU side of things, NVIDIA's Bluefield 2 is probably one of the flagship ones in the space right now. And this, again, 256 threads, 16 gigabytes of DDR5. And then one of the new emergents, and this is where I come from, is Achronix's silicon on Bitware's board, is a new FPGA platform that's got 750,000 6-input LUTs and 2,500 machine learning processors and 16 gigabytes of GDDR6. So there's a lot of computational power now in these platforms to consume that bandwidth and manage it. So what are they doing with it? Right? So the challenge we have is, excuse me, is that we're going to ask a lot of these GPUs and FPGAs. In the case of the SmartNICs or DPUs, a packet is brought in, there's classification done on the packet, we decide what to do with it. Do we have to decrypt it? Do we have to decompress it? Is there some sort of encoding that's got to be done on it, or decoding that has to be done on it in the case of a video stream? There may be further inspection that needs to be done for storage, right? Obviously, it has to go over to NVMe and be processed and put into a storage array, or taken from a storage array if it's a request. And then there may be additional actions you want to process against the data, right? So all of this leads up to queuing, because there's no way that you're going to bring data in, classify it, immediately pass it off to the encryptor module who's sitting there anxiously waiting for it. And the encryption module is going to do its decryption, and it's going to pass it off to maybe an inspection block that is anxiously awaiting for its arrival. Now all this stuff is going to be queued, and so basically it comes in, it's going to go out to DDR5 or GDDR6 or HBM2, where it sits until the block that is going to process it next is available. It's then fetched, processed further, possibly pushed back into storage, or memory, I should say, where it sits until the next block is ready, and so forth. So there's a lot of queuing going on with this. So where does all that queuing go? Obviously, it's going to go into storage, and we're pushing the edge of the memory systems that are out there now: DDR5, GDDR6, and HBM2, and soon HBM3. Each one of these has its advantages and disadvantages. Obviously, DDR5 is probably a cheaper way to implement things than doing the chip as part of the package from a perspective, from the perspective view of the end consumer. GDDR6 is, soldered down chips. All of these, though, have performance criteria that make them very attractive for queuing on these platforms. So what does that mean, right? We have a challenge with on-chip bandwidth, right? As packets or information comes in and it needs to be classified, it goes out to memory and waiting to be queued. So it's consuming bus bandwidth at that point. And then when the module that's going to process it next is available, it's sucked back in off of that memory. It's then processed and possibly even pushed back out again. And we've seen instances in the SmartNIC space, at least, where data is handled, in some cases up to 8 times before it actually emerges out the other end of the pipe and goes either, to the network or to PCI Express, right? So there's a lot of back and forth that happens. And why does all this happen, right? Well, it happens because of how we lay out chips, all right, from an architectural viewpoint. In the current model today, what we do is we take a 2D approach to laying out a chip. We'll put one block on one side that handles making, let's say, a connection to the network. We'll put another block on another side that handles making connection to the host. We'll put another block on another side that handles connecting to memory. And then we'll have other various blocks spread around the chip that do various acceleration, whether they're crypto engines or compressors or free programmable ARM cores or RISC-V cores or FPGA space. And we look at this from a 2D perspective, but the reality is it's like a busy city, right? Where you've got one highway that comes into the chip, one highway that leaves the chip, and then one intermediate highway that bumps stuff back and forth with to memory, whether it's DDR4, DDR5, or whatever. And so you end up with a tremendous amount of congestion moving the traffic around on the chip. So one of the ways to address this is to actually build a network on a chip, and a number of companies have done this. This is one of the reasons why I came to Achronix, because I thought it was kind of a visionary approach to the way they did it. What you generally do is you put all of your blocks that deal with the real world, your network interfaces and your PCI Express interface, you put those around the perimeter, as well as the memory connections that go off chip around the perimeter, so that way those pins don't have to be routed all over the place. You put them around the edge, and then you actually use a fabric that interconnects all of those exterior blocks, both peripherally around the perimeter here, as well as a crosshash north, south, east, west approach going across it. And what that allows you to do is, whether it's programmable logic or you were to put ARM cores or RISC-V cores in here, what you do is the programming blocks can then instantiate their own network access points, right, on either northwest or in, north-south or east-west, bus. And these buses are clocking along at 512 gigabits per second. They're 256 bits wide, so you can push quite a bit of data through them. And what this allows you to do is have independent compute modules that are not competing necessarily for on-chip networking bandwidth, right? Because you've got plenty of highway interconnecting everything. And that's kind of one of the things to think about as we move forward, with chiplets and chips in general, is how do we move stuff around on the chiplet, right, or chip, and then how do we move it between chiplets effectively, right? Because that's, the key is data movement in all of this. Also, there's programmability challenges, right? On the challenges side, obviously, it's tools, what open source tools are available, what tools work for the compute platform you're using, whether it's ARM or RISC or FPGA. Are those tools common across multiple platforms? What are the interfaces? Are the interfaces shared and common between them, especially in a chiplet environment, where you may have 2 or 3 different types of compute platforms in the same package, just on different chiplets? Are you going to have a common or unified development environment, right? And the timing of those modules, right? I mean, if you have a bunch of modules that need to talk to each other, communicate with each other, you need a timing mechanism and queuing mechanisms that can support that capability. On the opportunity side, obviously, open source has done an excellent job of filling the gap and meeting the need for a lot of these tools. New standards and protocols are emerging. CXL 2.0 has come out, and that's a way to take the massive amount of on-accelerator resources, whether in a chiplet or board, and share them more collaboratively with host CPU in a shared cache environment or memory environment or just a basic I/O. Thankfully, timing's flat. We don't have to go too much beyond 3 gigahertz. It seems like silicon has kind of settled down at that being the speed limit for the most part. And then we've got beaucoup amounts of memory to work with now, which wasn't always the case. So there's quite a bit you can do with all those resources. Security is both a challenge and an opportunity as well. As we do these new accelerators, right, we could theoretically take and push the storing of secrets off to a TPM, a trusted platform module, might be the host. Most chip designers would rather control things themselves and put an onboard secure root of trust that gives them their own secure enclave within which they can then manipulate keys and have trusted execution of critical resources and things that need to be done on the chip. And there are also physically unclonable functions, right? So a way to put secrets in the chip that you can only get out through trusted means. And then, of course, on the challenges side of things as well, opportunities, we have, libraries. What libraries are we going to put on our next generation accelerators? For example, AES GCM. What speeds do we want to have those libraries support? Because obviously, when you're licensing IP, you want to license it for the appropriate speed of the interfaces you want to connect to. And then, thanks to Spectre and Meltdown a few years ago, the whole concept of side channel attacks emerged. Spectre came from speculative execution, and Meltdown was a cache snooping method. And what these basically said to the world was that the chip could be compromised without ever having been removed necessarily from the server. And these side channel attacks are done using statistical methods where they look at power consumption, heat generation, in some cases even for other devices, sound and other methods, and they can actually, over millions of data points, they can collect and analyze and suss out keys and secrets. And so that poses a significant challenge for us moving forward. And there are defense mechanisms, countermeasures that can be employed that allow the security context within the chip to draw continuous power, so that way anybody that's snooping on power won't be able to get anything valuable out of that. You can also, by doing something like that, you can also keep the heat at a fairly consistent base. So there are a number of side channel countermeasures or SCA countermeasures. So I see the future as being pretty exciting for chiplets and accelerators. A lot of this, unfortunately, though, pivots around standardization. What packaging standards are we going to have? How are we going to handle the thermal issues and connection issues? Bumpless, stacked versus bumped versus just a bunch of wires. Obviously you got to consider pin placements and common pin placements for things. Then there's all the interfacing issues, the protocol between the chiplets and the host, and documentation. And this is gets a lot of doesn't get as much attention as it should. When you start having these chiplets and they're complex accelerators, it's not possible to believe that these documents are going to be several hundred pages. And we need kind of some common standards to say, hey, if you're looking for this, it's always going to be here. So we don't have to do an Easter egg hunt every time we want to try and connect two chiplets together and figure out why things aren't working. Common tools that are shared across chiplets. And then this brings in the whole ecosystem marketplace that JP was talking about earlier. As we move to an ecosystem and a marketplace, we need common tools and flows and simulation analysis that know how to deal with chiplets from different providers and to handle the thermal issues and the signaling issues and the interference issues, magnetic issues that may occur when you start stacking these high frequency parts on top of each other or next to each other within a given package. So I think the future is bright for chiplets and accelerators, and then I had some time today to give you a quick high-level view of some of the opportunities and challenges ahead of us. Thank you.
Thank you, Scott. A question that came in here, and I think it's a very important one. A lot of what you kind of referred to here is, sort of expanding that NOC fabric outside the chip as we look at chiplets. Mm-hmm. Be that, sort of no matter where, whose fabric that is. Can you talk about a little bit about what changes or what specific implications moving the NOC from a monolithic to chiplets? Your perspective?
So a common approach, I think, for this is an AXI bus, which is what Achronix is using. It's 256 bits wide, clocked at 2 gigahertz. Obviously, the challenge is going to be making sure that everybody pivots around the same type of bus architecture, the same frequency, the same signaling characteristics. I'm not necessarily sure that everybody is going that way, but that's what we've chosen so far. And also making sure that the distances and the wiring between the chiplets is not overly complex where it ends up creating a bunch of signaling and interference issues. Does that address your question?
Yes. And you want to talk a little bit about how you see the issues of power from your perspective?
It's always a challenging one. You know, as we look at these accelerators, you know, it's not uncommon for them to draw several hundred watts. If we go back to the NVIDIA GPU, where is it? You know, you look at the NVIDIA GPU that was just released, that's got to be, I believe, 250 watt power draw for the GeForce. The Bluefield 2, it's got some interesting claims for power, but you can see in the picture it's got a 6-pin auxiliary power here, so the 75 watts that's coming across PCI Express bus is clearly not enough to cover it. So I would say that most of these accelerator chiplets are going to be in the 90 to 100, 100 watt to 200 watt range easily. So when you start stacking those in a package, yeah, that starts to create a bunch of issues. So you're going to have to probably put them side by side, and then that creates distance issues and big packages with, you know, large amounts of heat coming off them. But I mean, that's, you know, that's kind of the, if you want this kind of power, you know, and this level of density, you're going to get those kinds of power draws.
Thank you, Scott. I think any other questions we'll have to wait till later because I want to keep us roughly on time here.
Excellent.
So thank you very much, Scott. And just to confuse things, we have a new Scott. So we're going to just switch Scotts dynamically here. So Scott Shadley from NGD Systems, I'll turn over to you.
Thank you. You should be seeing my screen as well, if you could confirm it.
Yeah.
I love GoToMeeting. There's 26,000 virtual platforms. So yes, I am another Scott. I'm in a slightly different direction. So I've spent a lot of time in the computational storage space, as you can see here. As a history of why it's important and things like that, I sit on the board of directors of SNIA, a partner organization that works around standardizations that is taking place within OCP and things like that. And I participate in the OCP storage work as well as some of the other efforts, and I co-chair the technical work group that SNIA is driving around computational storage. So today I was going to walk through a little bit, we're kind of shifting just a titch. I know the previous conversation was very focused around kind of the chiplet. This is a next step in compute, getting closer to storage, but not necessarily in the same frame of mind. So the next couple of presenters are going to be from our technical working group as well as members of OCP. And you'll get a different spin on how we're putting end products out there today that offer some new compute resources in terms of computational storage. So there's been quite a few introductory conversations about this, so I want to just make sure that I do a quick touch on it. There's a bunch of slides in my deck that will be published online. I do not plan on going through all of them. I want to make sure that I take advantage of the time and keep us on track as well. But the big thing is, we all know data is becoming the problem. And we can put all kinds of interesting things in front of data. We can store data in all kinds of interesting ways, but marrying the two ways to compute and manage that raw data is really where it starts to come into. And this iceberg of structured versus unstructured is a great way to look at that. There's so much data behind the scenes we all know we have to deal with that we're not doing a good job of dealing with in our traditional architectures that we have, which has historically been CPU, memory, and compute, and they've never been equal. And there's really no quite easy way to do that. And I think it was a great comment earlier from Samsung that made the comment, this type of technology is not replacing anything. It is augmenting and creating solutions for unique workloads in some cases based on the design of the solutions to solve our problem of how to manage data. It's all about compute, but it's really about the data itself. And so it revolves around how much data we're storing, where that data is located, and how we can act on that data. The results of the data are by far the most important aspect of what we're doing, but it's getting to that result. And we have a lot of different ways. We've already talked about them, and I'm not going to spend a ton of time, but we've got alphabet soup. So we've got GPU, we've got CPU, we've got NICs, SmartNICs, DPUs, all these different things. We've now got the new one from our friends at Intel, the IPU. All of these things are great solutions. They're all adding compute at different layers of the resources. They all have extreme value for what they're doing for the customers that need them for those particular workloads. But what's unique about every single one of these is none of these are data-centric, as in they require data to be gathered from somewhere to be put into some kind of local resident memory. And so the concepts of computational storage is how do we marry those things? In some cases, like the product I'm going to introduce, it's integrated. In some of their solutions, they're touching, they're closer, and they take the advantage of things like the resources that are available from different types of processing engines. So from a perspective of looking at it from a different light, there's a data distance involved and the gravity of that data. There was a comment earlier, a mention about 7 gigabytes per second over a PCIe Gen 4x4 bus. That's great for internal moving of information, but what if I've got to get it out of the box? Are the NICs capable of moving it at those rates? Some of them are, if you're getting into 100 gig, 200 gig NICs. You've got the smart NICs, which help integrate some of that. And you can see I kind of use this data distance on the left-hand side here to kind of highlight how they're all adding value, they're all getting closer to the data, but they're not integrated with the data. And that's what on the right-hand side is showing in this particular instance is a device that has an OS, processing layer, and memory all sitting with the storage device. There's no need, and the CPU of sorts, all riding right next to the data. There's no moving anything outside of that little box, that SSD solution. And the reason that that's of value is when you start looking at from a scale perspective. So very true what was mentioned by Mr. Park from Samsung. There is no CPU equivalent. I cannot put an x86 inside of an SSD. It doesn't make sense. It's not cost effective. And to the previous conversation, there's no way the power is available to make that work. But what if I put something that can help augment that capability and also take advantage of the networking limits that do exist in certain instances? So storing the data is easy. We've got hard drives, we've got SSDs, we've got tape, we've got all kinds of ways to hold the data. Working on the massive amount of data is becoming more of a challenge, and then moving it's even more so. So if you look here, if I take a 2 by 100 gig NIC, it ends up at 40 gigabytes per second with loss and everything else that takes place for interconnections between systems. If you're using a Gen 3 or Gen 4 device, your internal bandwidth of those devices is so much faster than what you can get out of the box, you end up limiting yourself. And this goes back to building networks into the chiplet and building other types of interconnects to solve our problems. Things like taking advantage of being able to be more lossless in ways with new interfaces and protocols. But it's also a density play. So as mentioned, you have 24 drives in a box. 4 terabytes is the average capacity today. 32 terabyte drives are out. 18 terabyte hard drives are out. How do we take advantage of that? Because we are needing that data storage, we've got to be able to do something with that. And this is where computational storage solutions come into play. So this is a graphic that comes from our friends at TechTarget based on some of the work done in computational storage. And you can see it takes that traditional architecture on the left. Center screen, we start moving the compute in different places. Compute in front of the storage. And we, in the computational storage working group, call that a CSP. There's other terms for it, DPU. You could even classify a GPU to some extent as that compute in front of storage. And then you have a computational storage drive, which was defined by the working group. And as you see here, the compute's moved into the SSD device itself. And so I put up here an example of how that could look from a rack level system. So if I had a 42U rack, I put a whole bunch of these OCP friendly 32 bay E1 short servers into that system. And I'm assuming there's nothing else but just a rack of servers. So yes, I'm taking some liberty with the numbers. I end up with 16 petabytes of storage when you put 12 terabytes per slot times 32 times 42. But with the capability that's added with something like the device from NGD that has a quad core CPU, I've got 4 cores of processing compute in each of those devices. You can see I'm adding over 5,000 cores of processing to the solution. Now, those 5,000 cores can do a lot. Again, they're not replacing the host CPU. Maybe on a core-to-core basis, depending on the type of workload you're working with, there's capability there. But this is a way that you can now truly scale compute into the architectures, because we need the data storage. Why not have the data storage do something more for you? And that's kind of where we came at it from the computational working group. So what's going on in that side of things? I know we spent a lot on OCP. I just give a quick rundown of what's going on in the other working groups. SNIA is driving an architectural document that's in a late stage release. It's out for public review for people to take a gander at. Our complementary protocol guys at NVMe have a computational storage task force. So SNIA is doing architecture, NVMe is doing protocol. We're working together. There's a liaison between those groups as well. You can see on the bottom right, we've got over 51 companies now and over 260 people that are helping participate in that working group effort. From a SNIA point of view, and an equivalent, basically, account in NVMe. And then the bottom left here shows all the different end customers. Because at the end of the day, we all as hardware vendors and standards body guys can do a lot of work, but if we're not getting customers to buy it, it doesn't really help it. And if we're not solving their problems, they're not going to buy it. So we've got things like US Space Force that have gone public with it. Los Alamos National Labs has gone public with their work that they're doing. The integrators, Dell, EMC, IBM, Lenovo, all these guys have different aspects of work that they're doing in the computational storage space. So with my SNIA hat on, I say I'm a proud member and effort of driving this type of work forward. So what I wanted to cover real quick also is just what else we need to have in the market to make this happen. I am a marketing guy at heart. I have an engineering background, so I spend a little bit more time on the pros of press. So we've got a lot of things that are happening out in the open market space. You can see even the industry analysts like Gartner, IDC, Forrester, 451 Research have all started tracking computational storage. You can see from the life cycle, the hype cycle graph, the life cycle of computational storage is early on. But we are there. We entered at a very high point on that graph because of the amount of work that's being done by so many different vendors that you're going to hear from additional vendors here today as well, and participants. So I'll jump ship just real quick and show you how we're doing it from a perspective of solving this particular problem. We've adopted the KISS principle. There's been a lot of talk about it needs to be easy to use, it needs to be simple to deploy, it needs not have to have hardware rewritten, software rewritten. So that's the premise that we took with this. It is an ASIC-based solution too, because we wanted to address the power and physical space issue. FPGA solutions are great. They have added value. They're quick turn for capabilities of prototyping, but from a deployability perspective, they do tend to take away some of the space available in form factors that are needed, like the new OCP E1S. So our particular product, because it is based on a quad-core CPU from our partners at ARM, we run a Linux OS. So our product literally becomes an SSH into and becomes that microserver that Mr. Park talked about from Samsung, but it is a tailored microserver. It does not do everything, and it cannot do everything. I can only run certain workloads on it and make it capable of addressing the solutions, but it has significant value add for a lot of different customer-based platforms, as you can see here today. I have a few different examples of actual customer use cases in this particular presentation that you'll get a copy of. I'm not going to go through a bunch of gory detail on it, but they are there for follow-up, and certainly if you have questions related to them. How we pulled this off, if you will, is we did look at it from a hardware-software ecosystem point of view. So we built a hardware device. It's a full-fledged NVMe SSD controller that happens to have a quad-core CPU sitting right next to it. We have extended memory attached to it, so the CPU talks to the CPU. If it were like copying an application from one server to the next, that's exactly what you do in this particular instance. We do offer a host agent, and the computational storage working group is actually developing a standardized API to help enable some of this work as well. In our particular case, we use the containerization capabilities. Since it's ARM versus x86, it does help with some of the solution solving there for our customers to keep it simple. And we've run a lot of different things. We found that specifically the way that our particular product was targeted is stored data needs to be evaluated. So store your data, then evaluate it locally and send the results back to the host. So we are kind of a store first, analyze second, send data out. It prevents the data movement that is causing all the problems with network bandwidth limitations and complications. And so we did that by having everything managed over NVMe. Nothing that we do with our device is outside of the NVMe protocol. And our software stack actually uses the age-old tradition of TCP/IP today to do that little golden arc or orange arc that travels over NVMe. So we actually embed all of the processing capability interaction from CPU to CPU through that TCP stack talking over NVMe. So as you're reading and writing to the device, you store data, you read data, do everything you want. If I want to analyze that data that's sitting on the right-hand side, I analyze it with the local compute and drive OS, and the result file is sent over NVMe instead of having to read out all the raw data. So bring in terabytes, send out gigabytes. That's kind of the process that's designed around this particular technology. And by having that ASIC-based design, we can also increase the density, because the more data you have in each of these devices, the more that local processing adds even more value. At 4 terabytes, 8 terabytes, you can move that pretty quickly, and a lot of the servers today have 4 and 8 terabytes of raw memory that they can allocate for that. When you're talking 32 terabytes or a petabyte of storage, being able to process that locally and reduce that data movement is truly important and valuable for the resources. So, as I mentioned, because it is a Linux-based platform and it is all inclusive of this particular device, it allows our customers to play around quite a bit. We've done things around compression. So we have the capability to add inline compression to our devices, both in incoming and outgoing compressed data. We've worked with a CDN company to do traffic routing, where we're able to actually make your little spinning wheel of death while you're waiting for something to load much more efficient. And then we get into the AI ML workloads of inferencing and distributed machine learning. And we've even worked with very memory intensive applications like Elasticsearch, and found a way to do a hybrid configuration. So very much to the point, not all workloads will be satisfied by this solution. There are ways to utilize the solution to augment a lot of different workloads. And I will tell you, caveat, we have a lot of workloads we don't work well with today, and that's just simply because the architectures are new, and those workloads being very memory intensive become very challenged to do work on storage side, because the CPU has to manage that data. And again, core to core, it's not a race. This is an augmentation, additive, supportive of that type of platform. One of the most noted is our project that we did with VMware. It's ongoing. It's been presented at their VMworld presentation as what they call the Office of the CTO X Labs. It's a accelerated platform off roadmap for early deployment. We're excited to have an announcement come out at VMworld 2021 about this solution and where we stand. So I'm looking forward to sharing that. But you can see this is a partnership between VMware, Dell, NVIDIA, ARM, and a bunch of different software solutions to create a very unique way of taking a rack-level database platform into an edge-centric two-server platform. Light capacity, similar performance capabilities, and yet we don't need anywhere the physical space or power consumption that's required for a traditional solution. So this is really where it takes the big picture into a much smaller envelope and still solves the problem. A particular use case that was highlighted here is ride sharing, and how we helped basically Lyft be able to reroute traffic faster, reroute the drivers faster. Microsoft and our organization and a few other research organizations put together this technical paper that was published in the ACM. As you can see here, I'm not going to go into detail. The article's available on our website, or if you want to know more. The big picture here is that big blue box. That is called loading time. That is moving data out of storage into memory for the CPU to process. The biggest value that we can bring from a computational storage point of view is removing that need to move the data and accelerating the processing. So 40 minutes of time on this particular platform was wasted simply moving bits from point A to point B for processing. The far right of that graph shows that that load time dropped to 1 minute. That's the success of computational storage in a nutshell. We also have machine learning activities that we can talk through. We've done object detection. This actually compares CPU, GPU, and computational storage side by side. So you can see the ability to get like accuracy for substantially less power is another very valuable solution for some of our HPC customers. So just highlight that as well. So I'll leave it at that. There are a couple more examples in here, but I know we're approaching the end of our time. So I'll jump to the end.
Excellent. Thank you, Scott.
My pleasure.
One quick question. You've talked a bit about, augmenting with very general purpose resources, cores. What is your thought on more special purpose, domain specific computational resources?
No, there are absolutely use cases for domain specific and needs for those. I mean, we can't make everything, one solution doesn't solve everything. We went with this general purpose concept here to get the adaptability and adoptability of the product ongoing. For example, the next generation product's going to have and one cores in it, which is something that was recently released in a chiplet solution from our friends at Intel. So domain specific is absolutely required, but there's plenty of general purpose options that are still out there for us to evaluate and drive forward in the architectures.
Thank you.
Absolutely.
Excellent. Well, thank you very much.
My pleasure. And we'll move off of Scott's now.
Well, I think it's all our Scots for the day. And do we have Professor Zhang? There we are. Excellent. So I'm going to hand over to Professor Zhang from RPI and Scaleflux.
Yes. Great.
Go ahead.
So I'm trying to share my screen. Yeah, so do you see my screen?
Not yet.
Okay, not sure whether.
Okay.
Sorry about it.
No problem.
So how about now?
No, I still don't see your screen.
Oh, okay.
Michael, anything you can suggest here?
Yeah, Tony, if you're sorry, Professor Zhang, if you're having any issues,
Yes.
I'm happy to share your slides for you. That would help.
Okay, yeah. So I'm not sure why I cannot. Okay, yeah, could you share?
Absolutely. Give me just one moment.
Yeah, so you do have my PowerPoints, right?
I do.
Yeah, great.
All right. One moment. Perfect. All right, you guys should be seeing Scott's slides here.
Yes. No, we're seeing the agenda.
There we go. And now,
Now we're seeing the slides.
perfect. So Zhang, go ahead.
Okay, so then how I can click? Oh,
If you just want to let me know, I'm happy to click through your slides for you.
okay, great. Yeah. So yeah, actually, yeah, you can just move, click a couple times. Yes. So it's really my great honor to have this opportunity to talk about computational storage and how it could really kind of benefit from the chiplet technology. So we all know that computational storage has a really kind of very beautiful rationale, like really kind of moving computation closer to where the data locates could improve the system performance, reduce power consumption, and etc. Intuitively, this simple rationale really makes a perfect sense and almost impossible to refute. However, like really in practice, so far is large-scale commercial success has remained quite like kind of elusive. And despite like in academia, we have already started this concept over 20 years. We have seen many like so many awesome academic research results, and over the past few years, hundreds of billions of dollars spent on its R&D, but still the reality is quite kind of disappointing. So yeah, could you go to the next slide? Yes. So then really this very disappointing status quo really cast kind of a big confusion and doubts around the computational storage, to be honest, that whether it is just another like academic fantasy, like many others we have seen over the years, or whether there are like any fatal flaws in this simple idea. So here we must be brutally honest to ourselves and admit that there must be something wrong here, other than conveniently like blaming the industry's like reluctance on embracing new and disruptive technology. So now let's see what the problem is. So can you click? Yes. So here, really the problem is that located at the very bottom, of the entire storage I/O stack, connected through the standard cross-layer interface like a POSIX, NVMe, and the SATA, computational storage clearly face pretty high and actually very high cost we call the abstraction breaking cost compared with other heterogeneous computing solutions like a GPU and a SmartNIC. Yeah, you can move forward. Yeah, so then and like in addition to this very high abstraction breaking cost, computational storage also face a kind of a big problem on its value proposition, or we call the benefit proposition. Really kind of different from other devices like a GPU and a SmartNIC. Computational storage by nature doesn't bind with any specific computation tasks, and different people could have a totally different vision and totally different expectation on its functions. So yeah, you can move forward to. So then this really naturally to lead to a kind of ambiguous and fragmented benefit proposition. So as a result, the computational storage really face kind of a much bigger challenge on establishing a commercially justifiable cost versus the benefit trade-off. Yeah. So yeah, the next slide. Yes. So then why do we still strongly believe in computational storage? So first, the bigger challenge on establishing a commercially justifiable cost versus the benefit trade-off is not necessarily an inherent problem of computational storage. Actually, it is caused by the intention of explicitly offloading the computation tasks through the entire I/O stack. So in other words, really the problem is a conventional mindset of that solely centering around the computational offloading. Yeah, so next slide, please. So actually all the existing successful heterogeneous computing solutions achieve their benefit through the explicit computation offloading. So it's totally understandable that people carry the same mindset to computational storage. However, as we know that computation offloading across the I/O stack really cause a very high abstraction breaking cost in the case of computational storage. So to successfully kick off the computational storage commercialization journey, so really the only hope here is to see whether we could move forward by dropping the mindset of computation offloading through the I/O stack. So yeah, the next slide, please. Yes, so yeah, you can just click a couple times to just finish all this animation. So then this really naturally leads to we call the in-storage computation that is transparent to the other abstraction layers. So this directly eliminates the abstraction breaking cost. And meanwhile, to mitigate the benefit issue, then we should have computation that have wide applicability and low efficiency of their CPU-based implementation. So intuitively, actually, it's very intuitively general. Could you click one more time? It's so very intuitively, this the general purpose lossless data compression is a very good candidate. So yeah, you can just click one more time to yes, thank you. So and then really like besides, it's almost like a universal applicability. Lossless transparent compression is the lossless compression is dominated by the random data access, and we know that the random data access will trigger a very high CPU cache miss rate. So that is fundamentally could lead very low CPU utilization efficiency. So then the in-storage transparent compression is, we would say, like, is at least one of the best ways to initialize the commercialization of computational storage. So then as shown here, yeah, you can just click all the way to, yes, thank you. So then as shown here, it can naturally also combine with transparent encryption. So by eliminating this abstraction breaking cost and establishing a clear benefit, so the in-storage transparent compression could easily flip this cost versus the benefit trade-off. Yeah, so next slide, please. So now let's really look deeper into the benefit. Actually, to most people, like in-storage transparent compression just means transparently reducing the storage cost, transparently improving the storage I/O performance. And so initially, that is also what we have thought. But actually, as we have done more and more research, we realize that there is the transparent compression actually opens a door for very exciting innovation opportunities that, however, has remained largely unexplored. So the more we could exploit this hidden innovation potential, then the more we could establish a favorable cost versus the benefit trade-off to practically justify the commercial value of in-storage transparent compression. Yeah. So yeah, next slide, please. Yeah, then you can just click all the way for this slide. Yes. So then first, actually, this slide just to briefly illustrate like where the innovation potential come from. Like for the normal solid state drive, like without transparent compression, then we should fill each 4K byte block completely with the valid user data. So this essentially leads to we call the fixed size block I/O constraint, and that is a big constraint on the design of any data management and management software. But in contrast, like if we have in-storage transparent compression, then we no longer have to fill each 4K byte block with valid data, because any unoccupied space will be just compressed away. And then as a result, we can pack any arbitrary amount of user data, like a 2K byte, 1K byte, or even like a 100 byte. So then into one 4K byte I/O block. So then this really leads to what we call a virtually variable size block I/O. So that means like even though we still stick with a conventional 4K byte I/O interface like NVMe and the SATA, the valid user data within each 4K byte block could have a variable size without sacrificing the physical storage cost. So this essentially break the conventional fixed size block I/O constraint. So intuitively, it could bring some very interesting opportunities to rethink the design of data management software, like a database and the file system. Yeah, so could you go to next slide, please? Yeah, you can click all the way through. Yes. So then in this context, really all the innovations happens in the applications, and we keep the existing interface across the entire I/O stack completely unchanged. So clearly, it is really highly desirable for the end user. So then, based on how much we need to modify the application source code, we can categorize the entire design space into three states. And based really here, we obtained very encouraging results. For example, like in the stage 1, we do not change we do not change application source code at all. We just simply change the, we have demonstrated like using PostgreSQL that we could leverage this feature by only configuring one parameter. We can improve the performance by over 40% without doing any source code change. And also like we can slightly modify the implementation of B tree to dramatically reduce its write amplification. So then that will make the B tree data structure almost perfect. That and then make the ongoing activities on alternative data structure like a log structure merge tree and RocksDB like really largely kind of useless. And then lastly, like we show that by leveraging this kind of very kind of transparent compression, we can design a new key store that really kind of has better performance and efficiency than any existing ones. Yeah, you can move forward. Yeah, to go to next slide, please. So then that really explains like why at Scaleflux we chose the path starting from the transparent compression. So our product is based upon, current product is based upon FPGA. And the next one, we already tape out our first SoC and we will launch our next generation computational storage drive based on this SoC next year. Yeah, next slide, please. Yeah, you can click all the way to. So then to clarify, actually, I'm not saying that computational storage is all about transparent compression. It is transparent compression is simply the best way to start the commercialization of computational storage, and we of course have a long way to go, and many in order to unleash the full potential, we still have a long way to go. Have many challenges and the innovation opportunities ahead, and so then within the next few years, then transparent compression will carry the computational storage into the mainstream market. So our drive is already being deployed in several hyperscalers and many like web scalers in their data centers. And then what is the next? What is the 5+ years into the future? Then we know that to answer that question, we should certainly look at what could happen in the future. Like certainly, as we already very known, like PCIe Gen 5, Gen 6 will be widely deployed. Chiplet technology will be widely available, and then CXL will be widely supported, and NVMe, this computational storage drive support in the ecosystem will be ready in 5+ years. So yeah, next slide, please. Then you can click all the way. Yes. So then at the Scaleflux, we believe that the chiplet technology will play actually will play a very important role for the next step, as shown here. That given the upcoming like a PCIe Gen 5 or Gen 6, the I/O bandwidth of each drive could at least be 16 to 32 GB per second. But the internal, the back-end flash bandwidth only peaks around like 4 to 8 GB per second. So the abundant, we could say like per drive I/O bandwidth make it possible to use each drive as a carrier to hold an additional accelerator that can be totally different, totally independent from the storage I/O stack. So that means in the same server, we have accelerator, we have one drive with the accelerator for AI and machine learning. Another drive carries another accelerator for video codec. And even the third drive could carry GPU or FPGA. So really like regardless of the specific function, so such accelerator can be called as a parasitic accelerator. That's really kind of enabled by the chiplet technology, and this very high bandwidth I/O for the drive. So then this is very well aligned with the CXL and the chiplet technology. So then we could really kind of move things forward. So yeah, so next slide, please. Yeah, next slide. Yeah, then you can click all the way. Yes. So then as the entire ecosystem gradually evolves, we will eventually replace the parasitic acceleration with integrated acceleration. Here, the attached accelerator could simultaneously carry out standalone acceleration that is totally independent from the I/O stack, and also the I/O path acceleration within the I/O stack. So then, such we call the ultimate computational storage drive will include the transparent compression, the parasitic acceleration, and I/O path acceleration. So then that will really lead us to the final stage of this we call the ultimate computational storage. Yeah. So yeah, next please. Yes. So this is the last slide. So then to really like in summary, like we believe that to change the status quo, like we must start from the transparent compression, and gradually we bring in the parasitic computation and eventually the ultimate computational storage drive. So this is certainly along an evolutionary path with many exciting innovation opportunities. And today we're still at the very beginning of the first phase. So to move forward, the chiplet technology will play a very big role. So yeah, this ends my talk. Thank you very much.
Thank you, Professor Zhang. Quick question. I see the clear path using transparent compression to sort of bootstrap the market from a hardware perspective. Can you talk a bit about the software perspective of how can you, I mean, do you see any way to sort of do similar bootstrapping?
Yes. So I think to bootstrap this computational storage drive from the software perspective, we have to start from where that we only need to change or modify one abstractor, the cohesive modification across this I/O stack. That will be face a too high cost barrier. So then from the software perspective, then the good starting point is that we start from this like relational database. In the relational database, the classical data structure, then we can just focus on modifying that data structure and to best take advantage of computational storage without worrying about changing the whole I/O stack. So that could be the best place that we can start from the software perspective.
Thank you. Thank you very much. Okay, so we're roughly on time. We are scheduled to have a short break now. So I think we're going to take a 5-minute break, and then we will come back and restart with David's presentation. So thank you all, and we will see you in 5 minutes.
Okay. How do I share my screen? Oh.
That.
Hey, David.
Okay.
Box, just like in rehearsal. There we go.
Yeah.
Go ahead and place everyone on mute for now, since we're taking a break.
Yeah. Oh, here we go. Here we go. There. How's that?
I don't see your screen.
You don't see it. Okay. Let's get that. No one. Let's try.
Now I see your screen.
Okay, so I just need to minimize me. There. Get rid of this. There. How's that?
Perfect.
but there we go. Okay.
And I'm going to hand over the moderator responsibilities to Bapi here.
Thank you, Gwen.
I'll let you decide when you want to formally. I think we're about 90 seconds left, but you can decide when you want to formally end the break and kick things off.
Okay, so we have 90 seconds. Okay, so we'll resume in 90 seconds. I have not timed it, Gwen. If you can let me know the time, then from that point, I'll take over.
So when I put in presentation mode, it seems to hang. Yeah. So.
Yeah, we are seeing in presentation mode, David, now.
Yeah. Okay. Well, I just hopefully this will be fine. Okay.
Yeah.
See, it's doing it again.
Okay.
And you don't see the control panel on the right?
No, we do not.
I'm not going to touch anything. All right.
Yeah, that's the trick. Once you get it working, just go with it.
Just walk away. Yeah.
Okay, I think that's about time to kick things back off. So I'll hand it over to you, JP.
Great, thank you, Gwen. So welcome back again. So we'll start with the talk from David McIntyre from Samsung. David, take it away.
Okay, great. Thank you, Jay. So I help to lead product planning and business enablement at Samsung for computational storage. And so I will dive right in. And I wanted to take more of a high level, set the stage view first. So why am I showing you this vast infinite data ocean? Well, my last check was that we're up to shipping 40 zettabytes of data, which is 40 trillion gigabytes of data this year. And just so the amount of data that we all realize through basically the explosion of applications and mobile data is huge. So that's the problem. That's the universe, the ocean that we live in today. So from a computational storage perspective, what do we do with all that data? Well, we have the responsibility to search through it effectively for the given attributes of each of the applications that we need to address. And there's no compromise in our urgency, how accurate our search is, how sustainable and reliable our tools are, and the results. The people that are on the other side of the applications, that's all they care about. So when we go through and build our underlying hardware and middleware and the applications themselves, we have to consider what we're building towards, because as we balance each of these metrics out, some will emphasize latency, say fintech for trading, whereas other might be the accuracy of the medical data that's being searched in a genomic sequence. Cyber forensics and security for sustainability, and results driven where maybe for real-time applications in ADAS or AI surveillance for security as well. So if we take that higher level perspective, now we can dive into computational storage and what that means to help solve this problem. So the compromise today is that we're dealing with latency, restricted bandwidth, expense, security and privacy issues, and resource dependencies. And the picture on the right shows that we have this vast amount of storage, which is our data ocean, if you will, and then a narrow funnel to transmit that data or the results of some compute through a channel, and then up to the data itself actually, and then up to the compute resources up in the cloud or on-prem. So we're relying on the compute resources that are traditional and basically tasked for all processing. We have this restricted network bandwidth that has to contend with not only the limited or bandwidth itself, but also the over provisioning of servers at the endpoint. And the expense for cloud instances, not only to lease these instances, but also for the egress of the data once we're done with our cloud service. Security and privacy, moving data around, such as medical data, maybe that's not in the best interest due to regulatory concerns. And then this misbalance that we're talking about. So if we get into the resolution, which is computational storage, we're able to reduce the latency because we're bringing the compute to the data for improved response times, where we can do the in-situ processing either on the drive or through an array of drives. We're saving on CapEx and OpEx because we don't have to ship that data as often up to the cloud, and we're also offloading the cooling costs and the host processor costs as well, which improves our total cost of ownership. And then from a security, privacy, compliance standpoint, we can manage localized data, process it on the drives, which provides better protection and control for our end users, and flexibility and scalability, where SmartSSD or any computational storage device can scale up from one drive to 2 drives. You can build redundancy, you can build an array of drives that are best suited to support customer application requirements. So the picture on the right shows more of a balanced situation. That's the intent, where now we can scale up based on the ability of having computational storage drives at our fingertips. So if we go through, what does that mean? So basically this gets to the next level where we're talking about these bottlenecks that we just went through, where we're either overloading the processor, we have to contend with more and more large scale data transfers. We certainly can offload to an FPGA or GPU accelerator. That is an option today, but I would suggest that with computational storage, you can get more scalability by building out an array of drives to support and process the data locally. So the deployments that we have to consider, one would be a compute storage server, where we're actually providing computational storage capability within as a adjunct to host server. We have the smart cache layer, where here we're providing fast storage with a compute element which can reside between the hard disk drive array and the host CPU. And then last, we have the cloud to edge, which many emerging markets there, but that is looked to explode in applications and use both with 5G and beyond. So basically collecting all that IoT data and processing it at the edge, either far edge or at an aggregation point, which can benefit from computational storage before sending out perhaps data, batch size data for post-processing up at the cloud. So this is one example of computational storage from Samsung. And so in this particular drive, we have a soft switch with a standard SSD NAND controller, and then the FPGA, it's a Xilinx FPGA, which is providing that compute acceleration function. This drive allows peer-to-peer communication, so you can basically make the drives autonomous from the host to some degree, and have sufficient DRAM and also storage capacity to not only store the function, the data, but also perform and process on that data. It's a fully capable NVMe interface, and basically it does everything a smart computational storage drive should do by providing full functionality for functional offload specific to data analytics, database acceleration, video encoding and processing, and data management such as compression and other storage functions for more optimization of the data. Here are some use cases. So we talked about database analytics. So for Spark acceleration in Parquet format, we're actually able to see a 5x performance improvement. And for Postgres, up to 40x faster performance in queries over a standard transmission where you're sending the data up to the host for processing. Also, another application would be rich media, where we're able to perform H.264 video transcoding and show 20% improvement in frame rate and offloading the CPU workload by nearly 100%, which is a very significant capability of reducing the CPU power, and then also accordingly reducing the cooling costs. And then this storage and big data services category would be being able to provide 3x decompression bandwidth, scaling up to an array of 24 computational storage SmartSSD drives in this case. And we're able to see the same regex search time for 10 petabytes as a 4 terabyte system as well. So the applications are growing and expanding, and we're seeing computational storage drives shipping in production today across many good design opportunities. This chart was created from SNIA, and it shows the build out from a security and risk standpoint, that if we look at these are functional blocks. So you look on the left side, you have a traditional storage device hanging off the bus. And then as we move to the right, we're adding additional functionality. So as we move to the right to the next block, we're having a memory function with computational storage functional memory added. And then as we progress through, we're actually adding the computational storage engine. And then to the right side, a full array of computational storage devices. So one thing to consider here is that are the risks. So a CSD, a computational storage drive, does have the ability with that FPGA or an ASIC potentially to delete, add, modify the data on the drive. So those are our risk insertion points. The CSD functionality can be programmed as well. And so the programming of the drive or the FPGA, that's also a risk intrusion point, as well as the virtualization aspect of managing the computational storage drives across an array. So some of the things that we can do, we can authenticate. So the host agent to the CSD and the other way are secure in that regard. Authorization, so we're only allowing certain users to have access through permissions control to the data and the drives themselves. encryptions, and I'll show an example on how to encrypt an FPGA, but that data can actually be encrypted by the CSD, and then auditing of the data itself to ensure that there hasn't been an intrusion. So there are some considerations here. The risks versus external accelerators as well. Remember, I showed you a picture of an FPGA or a GPU card. Here you do have direct access to the storage. You do have FPGA programming like you would with an FPGA accelerator card, but you also have direct access to the network infrastructure such as NVMe-OF. And the key point here, I think the layman's takeaway is that you are decrypting the data prior to processing the data, and that is also an exposure point. And going to the next. There, sorry about that. All right, now if we go to the device level and we focus on the FPGA security itself. So FPGA, they're SRAM devices, which are programmed by secure bit streams. We all know that. They can be programmed by either the host or JTAG port. Their bit streams are encrypted with the design tools that create the RTL and compile it down to the FPGA. FPGAs can be identified as either with encryption or no encryption for field testing. But typically, you'll see AES 256 being used for secure bit streams. So because of the complexity of FPGAs, well exceeding 1 million LUTs these days, now and pretty much acting as a system on chip, we can add additional countermeasures such as securing and isolating design regions. So you can take a design, you can partition it, and then put specific fault tolerance around each of those regions. Just-in-time partial reconfiguration, where you can modify the code within the design itself within the field. You can isolate the system on chip components within an FPGA. It could be a processor, it could be controllers, or any hardened elements. You can also isolate the bus, and programmable user files can also be defined to specific users or moreover to devices, and have dependencies put in place there. And last, just as the failsafe, you can have eFuses in case a condition comes across where maybe there's someone that should be using that device, that the device can actually blow a fuse. And there's a great article that I've got the link down there that talks about more of FPGA security for your reference from IEEE. So if we go back to the overall attributes of computational storage, at the beginning we were talking about urgency, accuracy, sustainability. Well, here we now have the ability of supporting low latency, data analytics solutions with full accuracy, providing product leadership and market leadership for sustainability of computational storage, and providing results with a performance value. That is, we're providing a more significant performance per watt opportunity than perhaps with host-based systems. We're also able to address security with data protection mechanisms, both at the subsystem level and at the device level. And our leadership, that is taking an opportunity with that 40 zettabytes of data growth, by developing innovative solutions and sharing our customer visions and listening across the applications from cloud to near far edge and to the endpoints themselves. So your invitation, those that are listening to this call, I'd say let's collaborate on workloads and use cases. Data analytics, data management, AI inference, video analytics. These are arguably the key lead applications that we can all collaborate on together to see how that computational storage can benefit and provide better performance TCO to our customers and the applications for each of those categories. Also actively engage in proof of concept trials. Of course, we're looking to align our trials with those production opportunities, but this gets us well into the hardware and software verification of using computational storage with across these different applications. Support your ecosystem partners as they come up with novel solutions and realize that they have different requirements from a business standpoint than large companies like Samsung do. So it's important to nurture our ecosystem from that standpoint to build out end-to-end solutions. And then also provide total cost of ownership comparisons to alternative technologies. I think computational storage drives can coexist with FPGA and GPU accelerators, but there's certainly, as they're coexisting, there is an opportunity to do that TCO due diligence to select the proper technology. And if you'd like to learn more, both on computational storage and what Samsung is doing in this market to position as one of the leaders here, feel free to reach out. There's my email address. And with that, that's the end of the presentation.
Thank you, David. So we have one question, computational storage devices are pretty interesting with FPGAs. How do you think the power would scale in future?
So the challenge with any power management across a SmartSSD or a computational storage drive, for that matter, is it's dependent. One of the key points is it's dependent upon the form factor. So a U.2 drive has a thermal envelope of about 25 watts. And there are other form factors as well, but using that one example, so that suggests that you're limited in the type of FPGA, the density of the FPGA pretty much that you can install on that drive. And with applications demanding more performance from computational storage drives, that suggests you might need a bigger drive and FPGA in the future, or some hardened host processing power as well. So those are all things that need to be balanced out. Some of the opportunity, as I mentioned, is if you move to different form factors that perhaps can tolerate more of a power envelope, then that can make room for more FPGA or other technologies that perhaps are more efficient with power consumption.
Okay, thank you, David. So next, let's move on to the next presentation. Next, we have Anand Kulkarni from Western Digital. Anand. Yeah, Anand, we can't hear you.
Yes, can you see my screen? I think I'm sharing it. I'm not sure it's showing up.
Yeah, we can hear you and see your screen.
Oh, you can. Okay, excellent. Hi, everybody. Thanks, JP, for the opportunity to talk today. My name is Anand Kulkarni. I work in the research team at Western Digital out of the Milpito's office. I wanted to use this chance to talk about an accelerator platform that we have been working on in my group. We'll go over a couple of target use cases, look at the video transcoding opportunity in little detail. To begin with, we've been working on an FPGA-based accelerator for some time. So what we now have is A Xilinx ultra-scale FPGA-based device in the U.2 form factor. We'll go over why the U.2 makes sense, but the design itself, as you can see in the block diagram, is essentially the FPGA is surrounded by peripherals, mainly 4 gigabytes of DDR memory, a couple of sensors for board management, and we have a USB interface for debug access into the device. The device itself is Gen 3 4-lane PCIe 2.5-inch small form factor, rated to 25 watts maximum power. I think each of these features makes it an attractive device to use as a compute accelerator. The choices of FPGA itself, as you can see, it gives you an FPGA fabric to work with, but along with that, it gives you complex of process cores to run firmware on. It has a bunch of hard macros, hardened IP, including a video codec IP and DDR controllers and so on. So that gives you a good match of a balance of ability to implement your own logic for whatever acceleration you might want to do. At the same time, not waste resources on standard functions and features that you would want in a system such as these. The U.2 2.5-inch form factor enables you to quickly deploy this in a standard server. Any server that has a NVMe slot for SSDs can now also host one of these accelerator devices, and that makes it a lot easier to deploy, qualify, and use it in your system. The 25 watts maximum power also is a conscious choice. I think if you look at any other standard FPGA-based accelerator platforms, typically you would use a PCI form factor, card form factor, which would be 75 watts, and it could be too much for your application, and you may not want to spend that much of a power envelope on your device. Secondly, PCI form factor, a card form factor means that you essentially cannot support hot plug. You have to open the enclosure, the server enclosure, to service it, and you typically have much fewer vacant slots in which to put an accelerator. And if you do have one, you would probably have other candidates for PCI cards that would go into the server. So it is probably easier to find an NVMe slot that can be repurposed for introducing an accelerator into your server. So that is a couple of reasons I believe that a U.2 form factor makes this compelling device to consider. In terms of the use cases that we are targeting for this device, the primary use case would be that for video transcoding. We'll go over this a little, but essentially useful in places where you may have few video stream inputs, but that you have to generate lot of output streams in order to satisfy a variety of viewing platforms. This is something that we are developing in partnership with Xilinx. A second use case which is very promising for this device is as a use for inference engines for both images or videos. Could be video surveillance, could be smart city applications, could be medical imaging. We'll go over a little detail of what exactly this use case, how exactly this use case is offered. A third one that we are chasing now is using the same platform, but as a computational storage accelerator. And I know we have heard a lot from the previous presentations today, a lot of good information on what this means. I'll just go a little over exactly how we would use our platform to prototype or implement some applications that can actually make use of computational storage functions as we talk about it. But in general, the choice of going in for an FPGA-based accelerator, it gives us, I think this list here shows us how versatile and configurable a single hardware platform can be in actually trying to target multiple different application domains. And the fact that we made it U.2 device allows us to deploy it quickly in a data center scenario. We have it qualified for use in data centers, and it's also very scalable because you can think of a server that has maybe 8 to 12 slots for 2.5-inch drives, and you could scale up. You can balance kind of the amount of compute that you want to add, or the compute acceleration that you want to add, in proportion to the amount of storage and the amount of compute that you can actually carry out on it. So you can build a balance by just quickly changing the ratio of storage devices to the accelerator devices in your system. So that also points to the flexibility that you bring into the system. To go over the first use case, we have an accelerator configured as a video transcode accelerator. This is something that we've developed in partnership with Xilinx. We essentially make heavy use of hardened IP in the FPGA that we picked, which has a video decoder codec unit, and it supports encode decode of both H.264 and HEVC streams. The accelerator function itself is integrated into FFmpeg, so essentially this shows up as just a minor change in the command line to any FFmpeg command that you may issue, and it transparently offloads the transcoding function to the accelerator device that it finds in the system. So you can very, very seamlessly convert your application from running on the CPU to running on this accelerator device. So as you can see, it supports inputs to up to 4K at 60 frames per second, or it could be HD video at multiple HD video streams, input streams, and you can generally configure the FFmpeg to build up a ladder where you have one input stream and then you have scalers and encoders used to construct multiple output streams at varying resolutions and varying frame rates. So, and effectively varying bit rates that you can generate the output streams. The performance, we'll go over the performance that we get from this device in a minute. Also, we get very good power to performance ratio on this device, and we'll show a little bit of data on that. Again, it is scalable. We can have a system that has up to 12 or even 16 such devices in one system if you really feel the need to scale up the performance that you get out of your server. This has limited availability now through Xilinx. If you look at the performance characteristics of this, you can see that very easily this beats performance of even a 32-core x86 server. The 32 cores, you get about 106. So this is tested using an example FFmpeg script that generates, it takes in a HT input stream and generates, I think, 8 output streams of various resolutions and frame rates. And for this particular script that we picked, a 32 core server can run at up to 160 frames per second, whereas a single accelerator device, for the Western Digital's accelerator, can get up to 220 frames per second in this system. If you look at the power to performance ratio, also you can see that it is a very compelling solution to look at. The 32 core server not only consumes much larger amounts of power, it also, the performance is also significantly lower. So the ratio shows up as a very good number. The next use case that I would like to look at is the machine learning inference accelerator. So this one is something that we have developed in partnership with Mipsology. They have a software stack called Zebra that comes along with it, comes with a FPGA IP that is available for our device. And using this, we can seamlessly offload any workload that is running either on the CPU or on a GPU. We can offload it to our accelerator. Any inference operation can be offloaded to the accelerator and enjoy significant performance and power performance ratios while running those inference layers. We support a large variety of networks. Really, the support for networks is dependent on whether you're using layers that are currently supported in the FPGA or not. But as academia generates new types of layers and new activations, they are continually integrated into the FPGA, and that enables more and more networks to be made available on the accelerator platform. Even in the case that some of the portions of the network are not able to be run on the FPGA platform, they can be split, and the compute intensive layers can be accelerated in the FPGA, and any new layers, unusual layers, layers which don't expect to be accelerated with run on the FPGA can be kept on the CPU. And this approach allows us to very quickly deploy networks and new networks on a system and evaluate performance. Now, I have a list of example networks that we can see the performance. All of these fit within the 25-watt envelope of our device for average power. Another use case that I wanted to cover today, and which is very relevant to what we are discussing today, is computational storage. And what we are working here is building up a platform that will make it easy to construct applications and application accelerators that can be quickly deployed on our platform and used to evaluate and also deploy for acceleration in the field. So what we are doing is implementing a framework that is implements an NVMe, the technical proposal 4091 that is currently going through the standards, and use that to offload compute closer to the storage devices. So we implement the NVMe stack here, and we implement the BPF. We provide a BPF VM that can actually execute any BPF object binaries that are sent down by the user application to be run on our device. And in turn, the software library can invoke accelerators that are present or instantiated in the FPGA. And what we are doing is developing a bunch of different example accelerators that can show various functions, including image analytics or database accelerations, and be able to show that we have a setup system where we can quickly reconfigure the accelerator into accelerating different variety of applications. And this is a project that is actively underway in my team, and we're making good progress on it. So this is my last slide. Just to conclude, we have just introduced a computer accelerator from Western Digital. We believe it is a very versatile device and a form factor that makes it very useful to deploy in a data center. Video transcoding is one compelling application where we see significant improvement in performance, at the same time lower power and cost, and less load on the CPU, so allowing it to be optimized for other applications. We also showed that we have within reach a lot of other potential applications. ML inference solution is available now. We have other projects in the works for looking at training at the edge and the TP4091 implementation, and peer-to-peer DMA to further reduce further get the benefit of computational storage in using this device. I'm open to questions if you have any, but if you want, please reach out to either Ted Marina or myself, Anand Kulkarni at westerndigital.com.
Thank you, Anand. We have one question. Michael, do you want to read the question or?
Yeah, sure. So the question is from Sean El-Bakuri. He's asking, I'm interested to find out the energy consumption of storage versus computational storage.
So I don't think I covered any of that, but I can give a generic answer in that bulk of the value would come from not pushing the data from the storage all the way to the server, but instead, if it can, the compute can be carried out closer to the storage, there will be energy saving from not having sent all the data to the host. As to how much the benefit is, I don't think I have data at my fingertips.
Okay. So the other question, and quick one, how do you see the compatibility of the applications with this kind of acceleration, the storage? Is there applications need to change, or do they understand there is an acceleration in the storage?
So there are a couple of different approaches in all these the three use cases that I talked about. I think the intent is to make it as transparent to the application as possible. How we get there and when we get there is open. I think the standardization that we are trying to do in the NVMe subcommittees is trying to get at least parts of it standardized so that they can be transparent to the application. But yeah, I think right now we are at the maturity of this solution is at a level that we are still having to do this analysis on a case-to-case basis as to whether we can keep the ability to accelerate or offload transparent to the application or not. Most of the time, the application will offer some plug-in interface that allows the software to seamlessly allow offload. But right now, it is still on a case-to-case basis.
Okay, thank you, Anand. So let's move to the next talk. So we have Professor Manohar Rajit from Yale. So Professor Manohar, please take it away.
Hi, thanks. Can you see everything?
We can see your screen. Oh yeah, we can see your screen, and we can, yeah, go ahead. You have it perfect.
Okay, fantastic. Well, first of all, thank you for inviting me to give a talk here. This is perhaps not necessarily exactly specific to the topic of storage acceleration, but this is based on something I've been working on for actually quite a while in a number of different contexts. And the emergence of chiplets.
Manohar, we can't see your screen sharing.
Oh, you can't anymore?
Yeah, and now we can see it, yeah.
Okay, this is strange. Let me change the screen sharing mode okay, I'll just leave it like this if that works.
Yeah, that's fine. Yeah, thank you.
Okay. So what I'm going to talk about is actually a collection of projects that we've been doing that together enable what I would like to think of as the equivalent of the app store for hardware or firmware, depending on your perspective. So what might something that's a firmware app store look like? Okay, so I actually think it should just look like a normal app store. I don't think actually, the point is the app store is just aimed at a user, and they don't actually care why that program is running. It should just, they just care about the features they're getting or the functionality they're getting. And this is just a snapshot from the Apple Store. I edited a bit to change certain things, but as far as the user is concerned, it should look the same. You could imagine a world where an application developer would develop their software. They would be able to post it to this app store, and over time they would add accelerator capability to their software that could be sort of downloaded by customers using an add-on of some kind, either based on the set of chiplets that exist in their system. Of course, the most generic way to imagine accelerating sort of any kind of computation would be to have something like an FPGA. So I'm going to use that as my driving example because that's also related to the project we've completed. But that's sort of the basic idea. Over time, a store like this, I could imagine, would collect statistics about how users, what accelerators users are downloading, and perhaps recommend a customized computer that a user could purchase for their next device, which would have certain, specialized chiplets that are available, as well as sort of the generic accelerator platform as well. So that's sort of what I've been thinking about. And the question is, what would it take to do this? A bit of background about what I've worked on in most of my career has been actually doing chip design. And it's sort of a sad thing to say, but I would say that I actually know what to build. That's not difficult. So the tricky part is how do you make it all work together and be transparent from a software perspective and an application perspective. Not just, I can build this fancy hardware, but if nobody can use it, it's not really that beneficial. So the projects I'm going to talk about sort of start out with, let's just talk a little bit about what are the different sort of requirements one might need for an app store of this kind. So the obvious one is, of course, instant gratification, right? So I want to be able to say, hey, I want to download this right now and see how it does. And maybe I have a free trial, and then I'll pay for it if I see some benefit. So what does this need? Well, to have the instant gratification support, you need certain sort of built-in core accelerators in your architecture that can be reconfigured in a pretty flexible way, right? So today, sort of the standard things people use for acceleration are FPGAs and GPUs. So let's just use those as the starting point, for lack of a better one. So that's why I'm going to think about that generic accelerator as being an FPGA of some type. For the 30-day free trial sort of mechanism, I need some sort of security mechanism. There are many ways to do this, handle the security aspects of it. Obviously, this is an important topic, but I'm not going to touch on it. So you need things like security keys and expiration and revocation rights and so on and so forth. So that's well studied in the cryptography community. So I don't want to focus on that today. The interesting thing is there's the one thing that actually makes this quite difficult today. And that has to do, I'll call it software support, broadly speaking. So this corresponds to two different parts. Okay, one of them is sort of how do I make my currently running application faster in a relatively transparent way? So you need existing applications should be upgradable. And I'll talk about sort of what we did to make that the case. So how do you make that work? The second piece of this puzzle is you need software developers to be able to create accelerators. And I actually think this is pretty important because, I mean, even if I just look at the numbers, by the way, the numbers I have here are from the latest Bureau of Labor Statistics numbers that were published a few months ago. There are about, according to the Labor Bureau statistics, there are about 22 times as many software developers in just the United States compared to hardware engineers in the United States. So there's a much larger pool of people. These are the ones who are actually developing applications. And so you want to enable these folks to be able to accelerate their applications. And you don't want to have to train them to become hardware engineers, essentially. So how do you go about doing that? So I'm going to talk about a few projects that we've completed that touch on some of these topics. So the first project we completed is a project which looks at FPGA processor integration as a way for doing acceleration. And this is not an FPGA and processor integrated on the board in some way through some bus like PCI Express or anything like that. This was an on-die integration where we could do whatever we wanted. We were working with actually we were working with a government lab. They had a multi-core system, and we designed the FPGA, and we modified both pieces of the processor as well as pieces of the FPGA to make this work together. And the FPGA processors were extremely tightly integrated to the point where you could do what I call a null function call, which is just a function call where you send in a value and you get it back. So there's no computation being done. But the null function call latency was, less than 10 clock cycles on this system. Okay, so this is sort of the level of integration I'm talking about. And the idea was there are a number of things you can enable, but if the integration is this tight, you could imagine offloading a small piece of code for acceleration. Not some massive monolithic function that's got heavy data use and things like that. That, of course, is possible, but this also enables the opportunity to accelerate a much larger percentage of the overall program. The other thing that's sort of interesting about this application is that this kind of level of integration is you actually need to leverage the strengths of both the CPU and the FPGA. They're good at different things, and you need them both, it turns out, to accelerate a lot of applications. This was a system where you had multiple cores, so there was concurrent access to the FPGA. So we had protection mechanisms built into the FPGA that allowed the different processors to access the FPGA concurrently without interfering with each other. It also permitted multi-program workloads as well as actually fine-grained reconfiguration. So you could literally reconfigure every lot independently on the FPGA if you really wanted to. Not sure that's a great idea or not a great application for that, but you could in fact configure an extremely small piece of the FPGA, and that was fine in a handful of lots. The other thing that was very interesting about this, the other enabling features that we added to this FPGA architecture included things like one processor could be reconfiguring a part of the FPGA while another processor was using the FPGA actively as well. Of course, you can't do that. The regions of the FPGA being used are conflicting, but as long as they weren't conflicting, this was supported. So you could have a processor reconfiguring the FPGA while another one was running some accelerator on it. That all worked. And we had a number of different interfaces to the processor, which were both polling and interrupt based. And we had a register based interface as well to the FPGA, which was the one we heavily used. And I mean, I'm talking about this was a chip that we taped out. This is sort of a snapshot of the layout of the FPGA. FPGA layouts are not exciting. They kind of look like grids. And you can't see anything anyway because of all the metal layers. If I had actually shown all the metal layers, you wouldn't be able to see anything. But this is roughly what the architecture looked like. So, oops. So how does the software work? So this is the more interesting part of this story. So we can build this FPGA. It's not a big deal. But how does the software really work? So the way we did this is we defined a set of FPGA calling conventions. So for those of you who are familiar with assembly language programming and the way compilers work, this is the same idea. When you call a function in C, there are a set of calling conventions that are used, the way you set up arguments and return values. All of this as well, there's a software convention that's followed. And so we had the equivalent hardware convention to pass arguments and get results back from the FPGA. And we had dedicated hardware that provided these virtual FPGA access ports. So you could have functions that had dedicated access ports. And so if you wanted to launch a function on the FPGA, you had a calling convention that said it's this access port and here are the arguments. And then you would get the return value back. Now, in terms of the software, the way it worked was that a function that was a candidate for acceleration would have a bit attached to it, essentially, a little bit of state that said, has this function been mapped to the FPGA or not? Now, if it's not mapped to the FPGA, you just follow the normal software path. But if it's mapped to the FPGA, you replace the call. This function is really a stub function, which essentially calls the FPGA function using the hardware calling convention and gets the results back. So you can think of this as essentially trampoline code, where you essentially have a stub function that either does the normal function call or just does a trampoline to the FPGA hardware, which runs the function and gets the return value. It turns out there are a lot of details to get this working. This is not a straightforward thing. If I were to just tell you about what had to be done just for this one problem, I would fill up an hour easily. But I hope the concept is pretty clear. Essentially, you call the function just like it's a normal function, and if it's mapped to the FPGA, you could do this. We also had a small runtime system that would manage what configurations were currently mapped on the FPGA. That was based on profiling information, and so that could manage the FPGA configuration. We ended up dedicating one of the software cores to just reconfigure the FPGA, to manage the FPGA configuration and do the bitstream writes and reads and so on and so forth. And we could do that concurrently with accessing the functions, so that were already mapped. So if you have something like this, then what you end up having is a lot of opportunity for acceleration, and you can also do the traditional accelerator. And the thing that was the other piece that was actually key to getting reasonable results in the platform like this was you need both a good CPU as well as a good FPGA. And it turns out that the expertise is actually quite distinct, and the fact that you could have a chiplet-based integration approach enables, you can imagine that top tier FPGA vendors could create chiplets for the FPGA piece, and somebody who knows very well how to do high quality CPUs could do the CPU piece, and then you could get the benefits of both worlds in some way if you could agree on this interface. So the second piece is, how do we get the software developers to be able to use a platform like this? And this is actually an ongoing project that we are working on how to map software directly to hardware in an efficient way. The project that we are working on uses asynchronous circuits as the target technology for mapping for the hardware. There's a reason for it. It turns out it's a very good match for the problem of mapping software to hardware, because when you write your C program, you don't insert clocks in it, for example. So it turns out that the sort of a data-driven mapping works quite much better in many cases, and especially for power. And that's kind of what we've been focusing on so far. So our approach that we are adopting takes programs and we map them into data flow graphs, and we translate these data flow graphs directly into asynchronous hardware. This is actually quite distinct from the mainstream commercial tools that do this, that work on this particular problem. It's called high-level synthesis, that basically generate a state machine based on your software, and then there are various options you can give the state machine to pipeline operations and so on and so forth. But fundamentally, they generate a sequential state machine, and then that schedules all the hardware and all the data flows and so on and so forth. So there is actually a much more important reason to use asynchronous hardware in this case, and that has to do with the fact that if you translate your software program directly into hardware implementation using this sort of approach, what you end up with is a mapping where your cost function for software and your cost function for hardware are very similar. So what do I mean by that? In software, if I'm running my program and I profile it and I improve a piece of my program, that's great. I've improved my program. It's a commonly used program fragment which I improved, and I'm happy I make that improvement, and that's my next improvement in my software package. But it's often the case that if you took that same computation that was described in software and map it to hardware, and you make some improvement, unless you've improved many parts of the hardware that were unrelated to the path that you improved from your algorithmic perspective, unless you've improved a lot of other unrelated pieces, you actually don't see a benefit. And people who've been by the way, this is one of the big challenges in high-level synthesis, and people have been working on this for a very long time, and it's just a very difficult problem to have the software do this all automatically. So because of this, a lot of people who write software don't like to use the sort of high-level synthesis approach simply because their mental model of what's an improvement doesn't translate. So they don't see this incremental improvement path. But it turns out that with this sort of data flow mapping, you do actually see that benefit. And that's because the path you improve, if you're using it, you see the performance of only the path that you activate in these asynchronous data flow circuits. And so we see that benefit. So we've actually developed a HLS framework. We call it Fluid for data flow mapping. And this is actually implemented in the production LLVM compiler framework. So we were actually taking straight unmodified C programs and C++ programs. And this is, by the way, this is a work my student did in the last year. So this is the starting point of our project, essentially. And we've compared the results that we obtained from our mapping to both what's considered the academic state of the art, and I always like to compare against the commercial state of the art, because often in these sorts of tools, the commercial state of the art is actually much ahead of academia, frankly. So we compared against both. And the results were actually interesting. I was actually surprised at how well we did, frankly, in this first pass. The first result I should tell you is that if you don't do anything and you just do this data flow mapping without any sort of specific optimizations, I mean, the LLVM compiler framework does a number of optimizations, but if you just take the result of that and then you map it, you actually get very bad results. Okay, so, and that's actually been reported in a lot of the literature. But in addition, what we did was we developed a number of post-mapped mapping optimizations where we do hardware-specific optimizations once we see the generated hardware. And after we apply those optimizations, it turns out that we see something quite interesting. So we actually see a huge reduction in energy for the computation. So the same computation takes less energy in the hardware that we generate versus the academic. Compared to the academic, we're significantly better. Compared to the commercial, we are also significantly better, but not as much as, but the commercial tools are just better than the academic ones. We pay an area penalty, and this is sort of an interesting setup. At the moment, we've been focusing on energy right now, so we haven't worried about area. The reason we save energy and we lose area is we get the benefit of specialization. So, for example, let's say I had two multipliers in my design, and one of them had an argument that was always 5, and one of them had one of the arguments that was always 7. Well, if I used a scheduling approach, I might pick one hardware multiplier, save area, and then have a mux that selects the two arguments, and then has a third, and the third argument is variable. But in our approach, what we end up with is we end up with two different multipliers, but then we can specialize the multiplier with that constant propagated through the logic synthesis. So we use commercial logic synthesis tools to optimize the data path, and so we see that sort of benefit. So as a result, we save energy because we get specialization, and then because every data flow element, the whole computation is asynchronous, we are only switching energy in the pieces that are used for your algorithm and not the entire circuit that's generated. And so the combination of those two factors gives us a significant energy improvement. It turns out we get better throughput, we get better delay than the academic one, but our latency is slightly higher than the commercial tool. So we get better throughput, we get better energy, but we pay a price, a pretty big price in area, I would say. But that's actually kind of what we're working on. It turns out that the biggest problem is one of the benchmarks that's a huge outlier. And we actually figured out why that's the case. The commercial tool has a very special case optimization for one of the arithmetic structures in that benchmark that we don't have. And so if we need to replace that, and then we'll be much closer to the commercial tools in that benchmark as well. So finally, you may have noticed that I said we mapped the target this to asynchronous circuit. So what do we do in terms of prototyping and measuring and getting confidence in our results? So in the past, we've always taped our chips. So we tape our chips, we measure the results. That's why we know we are doing a good job or not, as the case might be. The problem is the standard approach for prototyping is to use off-the-shelf FPGAs. So it turns out that we've recently been working on CAD tools to map asynchronous logic to a number of different technologies. So we've actually developed a full ASIC flow for asynchronous circuits. We use commercial tools wherever we can, and where we can't, we have our own CAD tools. So we have our own timing analysis and our replacement, for example, but we use the commercial router. But we also have a way to take our asynchronous design description and automatically map it to a synthesizable synchronous RTL, synthesizable Verilog state for vendor neutral FPGA mapping. And of course, we're paying a huge price for that, but at least we can get a hardware prototype up and running, and we can try it and see what we get from an architecture perspective. And because we were working with a government lab, it turns out that the processor we were working with was theirs. So we are now switching to using our own processor as well, so to build this FPGA prototype. So that's kind of what I wanted to give you a flavor from. I mean, so you can actually do this. We've actually built all the interesting ingredients for the system to be able to build a full system where you could imagine building a firmware app store. I hope I've convinced you that this is not a completely crazy idea. It may actually be possible. And we could imagine even prototyping something with existing off-the-shelf components and basically give me enough FPGAs and a nice integrated board to try this out. And we could probably do that. Tight coupling between the CPU and FPGAs and the appropriate API is important between the two at the hardware level and as well as the software level. And I think actually much more work is needed on what I'll call pure software acceleration, rather than most of the work in getting software mapped to hardware automatically, which is I would sort of put that in the camp of you're writing Verilog using C++, and they're doing it to improve productivity of hardware designers. But I would love to be able to I would love to see more work where you could just take existing software and see what you can do. So I'm just going to stop here. I'm happy to take questions. I just want to thank all my students who did, these are the key students who did some of the early work. And Rui is one of my current PhD students who developed this high-level synthesis engine. So I'll stop there.
Yeah, thank you, Professor Manohar. We are running short of time, but have one quick question. The idea of a high-level synthesis is pretty interesting for mapping to FPGA and chiplets. Can that be, I mean, most of the FPGAs available today, or almost all of them I'm aware of, are all synchronous FPGAs. Do you think the high-level synthesis can be mapped to synchronous FPGA and still reap the benefits?
You'll see some of the benefits. You won't see all the benefits. Actually, this is a longer thing. I actually think there's a much better FPGA architecture to be built, both synchronous and asynchronous for this kind of mapping. That would do a better job. But the problem in the synchronous FPGA mapping is it's the power that's going to kill you in this particular application domain. Because what you end up getting is a large amount of circuitry that you don't always use, and you can't always effectively clock it in a timely manner. So that's the challenge. At least the commercial tools are not clock gating it well. So I'm assuming what that means is that it's not so easy for them to do. So that's the challenge. Okay. But you could imagine paying a fixed penalty and doing an overlay. So I could build a virtual overlay on an existing FPGA fabric to map these sort of data flow computations. That's straightforward to do. I don't know what the exact power or what the penalty would be for doing that. I haven't quantified that.
Okay, thank you, Professor Manohar Rajit. Next, we'll switch to talk we'll go to the next talk from Stephen Bates. Stephen, are you there? Can you come up? Yes, we can see you, Stephen.
Hello, everyone. Can you hear me?
Yeah. So we're running behind time, but we'll catch up. Please go ahead.
Mine's going to be short and sweet, but I need to work out how to share my content. How do I do that?
Michael, can you help with that? Is it something you can enable?
Yeah, so Stephen, you've been made the presenter, but if you're having any issues, I'm happy to share your slides for you.
Why don't you share my slides for me? And that's going to be much easier.
Give me just a second to pull them up. All right. Let's see here. All right, you guys should be seeing Stephen's slides here.
Yes.
And Stephen, your slides were shared as a PDF, so I'm not able to put them into presentation mode, but if you want to go ahead, I think the attendees are able to see pretty well.
All right. Good. So we jump straight into slide 2. I think a lot of the speakers have already talked to this. I'm not going to spend a lot of time on it. We're at a very interesting point in terms of computer architecture. Things like NAND flash have really changed the dynamic of storage and how quickly we can get at data. Networking continues to grow incredibly quickly, but on the processing side, we struggle because Moore's law is slowing down and we can't scale as quickly as we'd like to. And then, something like things like Dennard scaling also mean that we can't run our single core, our single threaded applications as fast as we would like. And I think that's one of the reasons why we're starting to see a lot of accelerators in the data center. NVIDIA have done very well with GPGPUs. Companies like Google and Amazon Web Services are building their own chips. And there really is a desire to mix and match best-in-class accelerators in a variety of different ways to target a variety of different applications and customer requirements. And I think one of the very interesting things that this chiplet technology is helping to enable is that ability to go to a marketplace and say, well, I need artificial intelligence inference, I need regular expression, and I need video transcoding, but I don't want to go and buy a chip that has all of those and a whole bunch of stuff that I don't want. What I want to do is build something from chiplets that services my needs, and I need a marketplace and standards to go make that happen. So this is, I think, why chiplets are very exciting. If we jump to the next slide, I can talk to this one a little bit around why chiplets might be interesting for our company. We like other companies that are presented today are working in the area of computational storage. And one of the challenges that we always face is how do you build this, a silicon level solution for a whole bunch of different potential customers and potentially different applications, and you don't really know what the best silicon to build is, right? We don't know what the right accelerator mix is. We don't know what the right accelerator functions are. I think things like eBPF for more generic offloads are very interesting, and WD talked about that a little bit. I think that's a very interesting area, but programmable language-based offloads like that always have performance ramifications that we need to dig into. So being able to mix and match your accelerators is very interesting. One way we can do that today is with FPGAs, which is a technology that we at Adedicom use extensively, but FPGAs have limitations around power and cost. And so, what is interesting is, again, coming back to chiplets, is can I build something that has a mix of flexible FPGA-like architectures, but I can also bring in fixed function accelerators that are based on more of an ASIC flow. So I think that's really, really exciting. And, on the diagram on this particular slide is kind of a block diagram representation of products that we build. And what we find is that, we tend to have quite a kind of common base set of features that customers always want. But in terms of what they actually want specifically, there can be some variability there. So having chiplet technology available to us in order to do that, I think is very interesting. However, another thing that's really important to us at Adedicom is the software story around all this. So it's really great to be able to build things out of chiplets, but if you don't have a way of connecting that set of accelerators to applications in a standards and vendor neutral based way, then you're not going to sell very many of them, because your customers will be like, well, this is really good silicon, but I can't actually do anything meaningful and useful with it. So that's where another big part of our work and my work has been. That has been building an ecosystem around protocols for computational offload. You can call it computational storage, but it's really standardization of accelerators. How do we end up with a common framework for accelerators? Because one of the things I hear a lot from my customers is, we spent a lot of time and effort with our software developers integrating NVIDIA GPUs, we got good performance, but now we want to go try something else. But now I have to completely write all that software from scratch again, because NVIDIA's API is completely different to Achronix's, which is completely different to Xilinx's, which is completely different to somebody else's. Interestingly, we had a very similar conversation with customers, 10 or 11 years ago when it came to PCIe SSDs. We had companies like Fusion.io and others who were doing very cool hardware, but everybody had their own software solution. And we came up with an answer for that, and that was NVMe. So NVM Express is a protocol that is very successful and has basically eliminated vendor-specific drivers for PCIe SSDs. When I shop for a PCIe SSD today, I don't expect anything else except NVMe to be the driver or the API, for want of a better word, into that device. And what we've been doing at Adedicom with a whole bunch of the people who have been talking to us today is to push for NVMe standardization, not just for storage, but also for computation. And when we do that, we can do some very interesting things on the software side, which is what this slide is showing. And again, I'm not going to get into it in too much detail, but we provide a range of customer level solutions around things like database acceleration, transparent compression, software defined storage optimization. But we do it through a standard driver model using NVMe. And Scott from NGD mentioned something very similar. He said their products also use NVMe in order to communicate between the host and the device. And that's another company that's very involved in the standardization effort. So where we'd like to go with this is, have the chiplet technology on the hardware side to allow us to rapidly develop solutions for customers that really are optimized for those customers. So can I pull together a range of different chiplets, put that in a package, put in a PCIe or a CXL interface on the front end, and have something I can rapidly deliver to that customer that services their needs. But then do I also have a software story to go with it, which is the NVMe standardization component? And when you have those two things, you have the ability for a customer to very rapidly go to a vendor like us or like some of the other companies you've seen today, work with them to develop the silicon solution based on chiplet technology, but then also have the confidence that there's a standards-based, vendor-neutral software framework that's going to talk to that chiplet solution, and that includes upstream drivers in Red Hat and CentOS and Ubuntu. It includes user space libraries that'll work with all these different chiplets from multiple different vendors. And again, those libraries are packaged and available in your favorite Linux distribution. So it's a yum install or an apt-get lib computational storage or lib accelerator or whatever we want to call it. We have management interfaces that tie into things like Swordfish and Prometheus and other things, so that these devices can be managed and telemetrized at scale. And it also includes things like plugins for Kubernetes, so that if I deploy a Docker-based or a container-based solution, it can go out into the data center and say, hey, which of these 2 million servers has the kind of accelerators on it that I need to run this application, and can I get a couple of hundred of them in order to run my application, and have that all managed by Kubernetes or Rancher or whatever your favorite container at scale framework is. We jump to the next slide. Like I said, I'm going to keep this pretty short and sweet. This is just a customer success story. People are deploying these kinds of products. I'm looking forward to when we can bring chiplets in addition to just using things like FPGAs and SoCs. I'd certainly like to be able to build things out of chiplets, and I know my customers would. But customers are already seeing the benefits of deploying these kinds of accelerators. And without dwelling on it too much, we have things like reduced costs. One of the very first talks today was around TCO. It's really all about TCO here. It's about showing the customer that they can do more for the same amount of power and money, or they can save power and money and still get the same level of performance. If we just jump to the last slide here, almost the last slide, sorry. We are driving this NVMe standardization. Amazon Web Services were very keen to see this standardization occur. They helped to kick off this effort. They are a huge consumer of computer resources. The fact that they see benefit to a standardized framework for accelerators is really, really important. A couple of the speakers today have already talked about 4091. That's the code name for this standardization effort, and I am one of the co-chairs of that effort. If you're interested in learning more, reach out to me directly or one of the other chairs, or get involved through NVMe. If we can just jump to the last slide. Thank you, my slide person. That's the last slide. Chiplet technology, I think, is really interesting on the hardware side. We really need a software story to go with it. I think NVMe has a lot of potential there. I'm really excited about PCIe and CXL, which I think chiplet technology really plays into. And we haven't talked about CXL much today, but I think CXL combined with chiplets is very, very interesting from a silicon development point of view. And I'm looking forward to seeing more of this work happen. And thanks very much, everyone. If you have any questions, let me know.
Thank you.
Did I get you back on time, Jay?
Yeah. Thank you, Stephen. That was sweet. Stephen, I wanted to ask you the same question. Like we have some questions as well that you touched upon the CXL, right? So you talked a lot about NVMe as a protocol for acceleration. Where does CXL fits here? Do you see what role do you see in future for CXL for acceleration?
I gave a talk to a vendor yesterday that I can't name, but an in-house lecture, and that touched more on CXL than today. But for me, I think CXL is going to go to market initially as memory expansion. And there, NVMe doesn't have a big role to play. People are going to have a little chip that basically has CXL to the host and then DDR to a whole bunch of memory, whether it's persistent or not. And really now it's just a kind of a fancy DIMM with a lot of benefits from a power factor and form factor point of view. But I think what gets interesting is, as soon as people have done that, they'll be like, well, now that I have this, I probably want to move data around. So I probably need a DMA engine in this little chip that connects CXL to memory. And once you have a DMA engine, you might also be like, well, maybe I can do like compression on some of this data so that I save money, or maybe I want to do some encryption. So now I want to do a DMA and a bit of compute. And the types of compute people might want to do might get a little more esoteric than that. So maybe they'll start going, well, maybe I want to search this data using regular expressions or something else. And I think once you start getting there, then you're like, well, how do I kick off a DMA on a CXL chip? Well, I'm probably going to have to write a driver, and that driver is probably going to talk CXL.io, which is basically PCIe. And then you're going to be like, well, I probably want multiple cores to be able to submit DMAs at the same time. And when you start squinting a little bit, you're like, this looks quite a bit like NVMe, actually. So, the CXL.io is essentially PCIe. So without squinting too much, I can already see how an NVMe driver could program the DMAs on this CXL chip. And now that we have 4091 and a way for NVMe to essentially transfer requests to do bodies of work between the host and these little chip devices, it suddenly says, it sounds to me like, rather than every vendor writing their own driver for a CXL device, why don't we leverage NVMe and 4091 and use that? I mean, if I'm gonna do it, I'm gonna do it that way. And other people may choose to write their own vendor-specific drivers, but I'm gonna try and do it with an NVMe. And within an NVMe, without giving too much away from a confidential point of view, there have been several discussions around CXL is coming, NVMe is already here. People may want to build devices that can do bits of both. Do we, as two different standards organizations, need to be liaising and seeing what needs to be done to make that work as well as it possibly can, right? There's nothing I can talk about publicly on that, but these discussions are being had and have been had. And I have no doubt that people will build silicon that talks CXL to the host, but requires a driver using CXL.io, and it will be doing DMAs, and it may be doing compute. And NVMe, I think, has a role to play in the programming interface for those types of devices.
Excellent.
Yeah.
Okay, thank you, Stephen. Thanks.
Yeah, thanks a lot.
Yeah, we'll switch to the next talk from Ravi Swami. Ravi, are you on? Can you come up, please? Michael, do you see Ravi? Yeah, Ravi, we see you on the panel.
Ravi, it does look like you're muted, so if you could unmute yourself. And then we are seeing your screen.
Ravi, I think we can see your screen. I see your screen, but we can't hear you.
Can you hear me?
Yes, now we can hear you.
All right. Okay, great. Can you see the screen or?
Slides, Ravi, yet.
Yeah, hold on.
By the way, Ravi is talking to us from India, so thank you, Ravi, for staying late night for this talk.
Hey, thanks. Yeah.
We can still see your screen, but Michael can help you if you need.
Yeah, a second, hold on. So let me try to get the presentation up, but this is on set. So
do you want Michael to share the slides, Ravi?
Yeah, hold on a second. Yeah.
Sure. Yeah, we're seeing your screen, Ravi, but I don't know which screen you're sharing now. Yeah, now we can see your slides, yes. But
all right.
Can you put in the presentation mode? We're seeing 3 slides together.
Doesn't give me the option. But well, this is viewable. I mean, that's the most important thing. I mean, like, I'm not sure if you can see me in any way, but are you able to view me?
Yeah, we can see
or?
your screen. Yeah, we can see
Are
your
you
screen.
able to see me?
No, we can't see you.
All right. Yeah, I don't know how to get video here. Is there a way to get video or?
Hey Robbie, yeah, I'm not seeing that you have a webcam enabled. It may be because you're on your phone.
Yeah.
No, So I'm not seeing a way to enable a webcam here, unfortunately. But we can hear you, and we are able to see your screen.
Okay, it's all right. Yeah. Okay, cool.
Yeah, hey, Ravi, Ravi, your screen switched. We're not seeing the slides anymore.
Yeah, hold on. Okay. So one of the things I want to talk about here is like I did hear about the Play Store or whatever was there. You know, like creating a Play Store for devices and chiplets. That was pretty cool, but really what I want to focus over here is like Ceph. The reason why I'm choosing Ceph is because of it's a distributed object store. Not only that, you can also like do an an S3 select or something on an actual device, which means you're moving down computation down to an SSD. So creating a distributed architecture is something that I'm looking at. And doing that, given an ARM processor we have, we can actually like, you know, create a completely distributed system where you're able to move computation down to unit, but at the same time, you're running a microservices architecture. And this is one of the things that I was looking at, like given the whole deal with the software problem that's happening here, where people are trying to use like eBPFs and the rest of the drivers and like, you know, going through a whole lot of stuff there. It's simpler given the infrastructure to just like evaluate the system based on creating microservices. So the reason I'm saying that is that it's easier given a segment like Ceph, right? So Ceph gives a completely distributed system, an object store, as well as a access mechanism where you can access the gateway and actually offload the data down. In addition, you have like things like redundancy and erasure coding that actually runs within the system as well.
Sorry to interrupt you, Ravi. Ravi, we are not seeing your slides anymore. You're seeing a blank screen.
I'm sorry. You see now?
No. Yeah, now we can see it. Thank you.
Okay, good. Okay. So I really wish the webcam worked where I could like show stuff, but no, I don't know why it's not working here. But I'll go to the space where we look at, let's look at this one. So you have an object store, and given the bandwidths we have, I'm not sure if everyone here is aware of Ceph and the rest of the architecture, but I hope it will be more interactive. The rationale here is that we want to move something like predicate push down actually down to the individual devices and offload them off. And given the software architecture, I'm like trying to understand like if we can make a platform where it's more distributed in the sense that we do have the chiplet-based system that's available today and the hardware, and something like Ceph would run on it, and we can go through like Ceph and the rest of the things, but but it's a little complicated based on licensing systems. So so given that factor, I'm thinking like there'll be an evaluation platform where we'll deliver it to you, where you can like run a distributed object store with an access to ARM processors. So so one of the things I came up with is you got the Xeon cores here that's running, and then you have the PCIe bus, but at the same time we have a whole lot of SSDs running here, and moving down Ceph and OSDs, which is basically an object store, is quite simple. If someone's downloaded the software and things, I mean, it's easy to make a gateway and run it. But the problems there that occur is like things like RAID-OS and as well as the infrastructure that's there with so today, for example, like the gateway actually runs on the Xeon, which is centralized. So the RAID-OS gateway actually runs on it. That means like it runs like a little web server on the Xeon. But moving that down across different systems makes it a little bit tricky. Are you guys able to hear me? I'm not sure.
Yeah, we can hear you, Ravi, but the screen goes in and out.
Okay. Yeah, I don't know why I'm presenting it from the phone, but so the goal here is more to, if you come in from the internet, you have the PCIe and you have the Xeon cluster. At the same time, we need the devices to communicate with each other. And one of the benefits we get across that is using something like CXL. And to build such a platform, it's important to make these individual units addressable. That means if you're going to scale up like a single rack unit, which is basically a 2RU rack unit with 24 SSDs, it's probably impossible today. It's really impossible. It's not absolutely impossible. Even if you take the kernel apart and move it across, break apart software, it's like something you'll never make because it's like you're building drivers here, there, and it's everywhere. It's like like splitting software across. So one of the proposals I have is like to make a microservices-based architecture just for evaluation, nothing else. It's just for evaluation to see like how much compute you can move out or distribute, and it gives an interesting platform where you can actually like move across this whole segment of software without breaking it apart. A lot of effort goes into breaking it apart. And one of the key areas that is required in software is that you need to like have it addressable, right? You think of everything else like a microservices, but the problem is like how much compute can you have? How much power can it have? You can't run an entire web server on an ARM processor in a power envelope of 20 watts. You can't do that. But at the same time, you do have shared memory accesses between the individual devices. So that opens up an arena that creates speed of redundancies, and you don't have to like go through like a different area to actually a different server or somewhere else, go up to the Xeon or another web server to just move in blocks of data. Now one of the things with Ceph is that it's moved on. So Ceph has moved on from using the file systems beyond just the file systems. They're using nowadays they're tending to use like raw data blocks. So they're actually getting down to the SSDs. They're getting to complete raw data, and that means that they're going away with the file systems that we have today. You know, like ButterFS and the rest of them, and that's a good thing because they're using key value stores from RocksDB and other things that lie in there, and it's more efficient. But at the same time, it's like what I want to get out of you know, some of the things in the presentations I've seen, a lot of them, is that is there an actual development platform that would be useful? Something that would be useful where we can build in and allow compute and evaluation of the system as such, and move in segments. And one of the things that I was looking at is like addressability as well, like microservices, where you can actually address the individual devices as such, like it's an individual server. And that takes out, you know, like OSS, all the problems that we have today that are, you know, like breaking apart buffers and trying to, like, you know, move them down to another card somewhere else, because the bus speeds are like humongous, given like, you know, CXL and things. It's really high speed buses, and just running a, you know, an IP over that makes it a complete network system. And that's one of the things I was wondering if that would, if we deliver something like this, would it be a platform where people would come in and use it and evaluate, you know, distributed software that's there today? And that's something that's easy to do. So this, like Ceph, we're going to evaluate it on the way of performance, and I think we'll give some numbers pretty soon, and based on this platform we have today. But these are questions that need to be opened up, like really, like which is the direction and where we're going at. I think like most people are aware about distributed databases today, but our objective is to demonstrate as simple as, you know, like use the Amazon S3 API and like do a query down that actually bypasses the whole CPU and goes to the actual SSD, and that's one of the goals we're trying to do. So yeah, I'd like to open it up to questions if there's anything else on that.
Okay. Yeah, thank you, Ravi. Yeah, one question. So the proposal that you're making here, the distributed system, the self-implementation radars, what does it take to implement that in the open accelerator hardware that we talked in the morning? Do you see as a good platform, good fit, or what does it take to implement your proposal?
So one is access to the hardware. Mm-hmm. Another is creating actual reality. That means like, you know, probably an open source project or a GitHub repository where you're able to distribute OSDs and, you know, the monitors and figure out how it works, right? And how much power it can take, and what is the easier mechanisms rather than going from one PCIe SSD connected on the bus to the whole CPU down back. Is there like a shortcut, in terms of bus speeds and bandwidth? And yeah, it could be CXL, it could be something else. But that opens up a whole thing of distributing software where, like it offloads in entirety, almost like middleware from the whole CPU down to the rest of the system. And and that's it. And of course, like that's something we have to try, but there's a platform that we have available today where we can actually accelerate that. So
okay,
I was thinking like doing a demonstration of this would actually like show reality and getting it on the platform working.
yeah, that'll be cool, Ravi. Thank you.
Okay.
Okay, let's use the time. Let's switch the topic, and then now we'll have a panel, end user panel. That Quinn will moderate and run the session. Quinn?
Yeah, well, I want to take a step back, and the goal here at the end here is, we came into this, ODSA is all about, does someone want to turn off the screen share from Avi there? Michael, maybe you can override there. I'll keep talking. So we came to this, ODSA's charter is to push domain-specific acceleration standardization, specifically around chiplets. And as a work group in that, the prototyping and proof of concept group has been working on building this new domain, this open hardware model where we can prototype chiplets with little daughter cards to build go through the process of what it will be to build chiplet solutions before we actually have chiplet hardware today. And that's why, and we're really excited the fact that we now have these boards, we have the daughter cards, we've got 3 different people who've created workable cards that go onto this prototyping platform, and we're hoping to get more. And now we really want to try to reach out to the community in large and try to engage people, and we think that computational storage is a good starting point for that, but we want feedback from everyone on, is that a good starting point for using this new prototyping hardware? What should we be looking at in computational storage? What other areas should we be looking at? And how can we get more people involved in building on this new hardware? So I want to put a few poll questions up first, just to take, these are very quick multi-choice questions. Get people's thoughts based on today's presentations real quick. And Michael, if you wouldn't mind posting the first poll question. And I'd appreciate if everyone would just very quickly click through here. And Michael, I guess if you could show the results as we go here, maybe.
Hey, Quinn, yeah, so we can show the results as soon as we close the poll. So let me know when you'd like to.
Did you see how many people have completed?
Yes, so we've got just under 50% of the attendees have completed so far.
Okay. So some of you probably walked away from your keyboards. Please click on through if you don't mind. We'll close it here in a minute. Let's just go ahead and close it and move on here. So, results. Okay, I can't see the poll results. Can everyone else?
Hey, Quinn, so yeah, they are being shared with the attendees. We came in with 20% saying yes, 50% answered maybe, 5% no, and then 25% don't know.
Don't know. Excellent. So, okay. I apologize. I guess I should have had an attendee screen open too here because I can't see that. But excellent. So it does look like there's some interest here. And we are going to be, just for everyone who's interested, we are working on how to make this available and hosted so that we can put this out to the broader community and get everyone access to this hardware. And those, we'll be putting out various ways to contact us and get engaged with that. The second poll question, if you wouldn't mind posting that. So one of the things is we have these building blocks. We have, you know, the NIC. We have the NXP has given us a really powerful ARM core complex, and we have the Lattice FPGA. But we're interested if other people out there are interested in making more cards for this, because the more cards we can put on this, the more robust set of solutions we can build, the more varying solutions we can build. So we're just kind of getting a sense of how interested people are in creating their own cards for this solution. So I'll trust you, Michael, when you see the completion.
Sure, we'll just give it just another minute or two here. Currently, we're pulling a 8% yes, 60% maybe, 0% no, and 31% say it's not applicable to them.
Which is fully expected. Not everyone has silicon to make sense of this, but it looks like we have some yeses. So, you know, definitely those people, we're really interested to talk with you and see what hardware you have. And, you know, we've tried everything we can to make this an easy path. So we have references, we can give you the existing board schematic for the connectors and all of that to try to make this as smooth a process as you can. And I guess, any of those yeses there, can we let everyone chime in and unmute their things on thing? I'd love to hear anyone who has a yes there talk about what they're thinking of chips they'd like to maybe bring in.
There we go. So folks, you are now able to unmute your mic if you would like.
Is there anyone out there who'd like to share what they're thinking about as chips that they would think about bringing into our prototyping environment here? This is the interactive session. Any brave souls?
So we are getting a question in the chat, Quinn. It's from Gary Greider. He's asking, does the environment allow you to put a chiplet between memory and the processor?
You know, the prototyping thing here, and this is our first generation of a platform. To some degree, you can, but you'd have to put the memory on your own little daughter card here, because then you could put the memory. You could bring the memory and put it in to your daughter card, and then prototype solutions where you have a smart agent between the host and memory. But we don't have. Well, we have the flash drives, but we don't have say a DRAM bank here that is on the main card itself. That's a good question. And our goal was to build, you know, we can't build something that can do everything. We tried to cover as much as we can. And then let's get the next question up here. And so we're interested if people think computational storage. Now, we kind of want to, we went down this path, but we're really curious if people think that maybe there's other directions that are better. It looks like a number of people think this is a very interesting first direction of prototype. Clearly, this hardware is not built specifically for computational storage. It can be used to model lots of different solutions. And I'd love if anyone from the no side would be willing to say why they think computational storage is not a good first thing, because that's the kind of feedback we're looking for to help us make better decisions for the prototyping effort here. Could anyone from the no side be willing to share why they think computational storage is not? Anyone? Okay, I guess.
Yeah, I'll join in. So you mean when you say, is it a good first vertical to explore? Computational storage is more of a technology that provides a solution to verticals.
That's a valid case. So what do you think we can do to narrow it to get more people involved and interested and make the results more relevant?
Results on performance and applications?
Well, so I guess to say we're trying to prototype how chiplets disaggregated solutions are beneficial in this space. What is it that we should be trying to show in terms of the hardware and software stack that would de-risk chiplets and for these kinds of application spaces?
Yeah, my opinion is it's more market enablement by the technology, the underlying technology. So, many of my colleagues have shared POCs and solution results across this morning. And so, chiplet technology is just another, it's an addition to an enhancement perhaps to computational storage is just another option for us. But, as far as the computational storage itself, SNIA, NVMe, all the standards bodies were referenced, and many of our partner companies were also, or colleagues were also mentioned and participate actively. That builds up the standardization side, and then just reaching out and building out POCs and solutions that can test the requirements of these vertical markets. So, chiplets is way down in the stack, but certainly could provide some value.
And are there workloads you think in the computational storage domain that are the most interesting or compelling for people to see explored?
We referenced across the morning, we talked about artificial intelligence, video processing. Chiplets provide a flexible approach, even a more flexible approach to address those areas. Yeah, so those are two examples, but there are many.
Yeah.
Yeah, but video, data analytics as well. Video is a piece of that. Those are what it seems like, the leaders that are, the first ones out of the chute for computational storage are focusing on.
Excellent, thank you.
You're welcome.
I just want to open up now for anyone else to just hop in on their thoughts on this effort and what you feedback for us in terms of this prototyping effort and where you think you'd like to see it evolve. So if anyone has
quick reminder to attendees, you've been unmuted, but that just gives you the ability to control your muting on your end. So if you'd like to converse with our panelists, you'll need to make sure to unmute yourself.
And I would invite, you know, JP, Bapi, if you guys want to join me, Young, go ahead and join me here to.
So
Sure.
it would be nice to get anybody's thoughts on chiplets that you'd like to see built. Oh, sorry. Hang on, Mike.
And Quinn, we are getting a couple more questions and comments coming in.
Okay.
Mr. Grader here. Gary says, so demonstrating a processing pipeline that uses multiple chiplets might be useful. Useful in stream-oriented applications too. And then goes on to say he thinks that being able to read memory in a different order than that it is written is important. Thinks scatter gather operations across lots of memory, scatter gather, and memory atomics.
Yes. I think, you know, especially using multiple of the NXP chiplets, pitchlets as we're calling them, they're little daughter cards. We could potentially prototype some of that with this right now. Because we can, you know, have multiple of those that are then streaming data between each other and using their memory as a model for a larger system memory.
Mm-hmm.
So we're kind of at the end of time. Bapi, do you have any sort of final words? I want to make sure we invite everyone here. You know, we're going to be sending out a follow-up survey, but we're also, you know, everyone here, you're welcome to check out the ODSA wiki, join any of our ongoing calls and working groups. We're always looking for more participants and more help as we're looking, especially in this prototyping area. And Bapi, do you have any last words?
Two things. One is, well, actually three things. One is, you know, the other thing we're certainly looking for some help on or suggestions on is if there's any particular software framework we should port to what we have, that will make participation much more productive. The ideas we were sort of pushing around were SPDK as an example. But if there's something else we should be looking at, I think we're all pretty open to that. Two, please, if you have any follow-on questions, any other suggestions, you know, please send them in by email, and we will address them by in a follow-on meeting. Please do join us for our weekly meetings and join the POC effort. And finally, a huge thank you to JP, Quinn, Ravi, Young, Michael for pulling this together. Thanks a whole bunch.
Great. I was just curious, like, can we like have like little like talk about like, you know, the software offloads and the framework that can happen? Is it a different forum or something that people would want to create?
I think we can certainly do it. Absolutely.
And probably the best way to start that is just to bring that into probably our weekly meetings, and we're happy to.
Yeah, these are more detailed discussions, and it involves a lot of, you know, the flow. So
yeah, but we can start there, and then that we can use that when we identify the, you know, sort of when we need a longer working session.
All right. Yeah. Cool. Thanks.
Yeah, thank you. Thank you, everyone.
Vijay, you're muted if you're trying to say something.
Yeah, I'm sorry. Yeah. No, I just want to add, if anyone wants to, have access to the platform, they can actually sign up to the Google Sheet. We are just planning to put it on Google, and then we can give them access. And then we can also do some live support, so they can just try the platform out as is right now. And once it gets hosted, I think they'll have a hosted access, and then they'll be able to develop their systems on that. And the other thing I want to say is, if they need any help, if anyone needs any help with the pitchlets or any other work they're doing, they can please feel free to reach us through tamind.com, and we are more than happy to help you guys. Just want to add that. Thank you.
Yeah, I'd like to thank all the speakers who participated. So a lot of very interesting, lively talks. Thank you so much. Thanks for the participation, both from the audience and the speakers.
Thank you.
All right, thanks all.
Yeah, thank you.
Thank you, everyone. The slides and recording will be shared with the attendees likely early next week. So you can also go to the ODSA wiki. It'll be posted there as well. If you asked a question and the panelists were not able to get to it today, they'll be reviewing all the questions following this webinar, and they can reach out to you directly. But yeah, encourage you guys to get involved with the great work that the ODSA is doing. Appreciate your attendance.
Thank you.
Thank you.